off. There you are. Yeah, I checked it when I turned it off, right? Yes, yes, yeah. Ah. Yes, you can see. Okay, yes, that's like, oh, yes, you can say like, oh, Peter, how can you be so stupid? Yes, yeah, I also think that. Check the microphone and then forget it to enable that. Well, anyway, anybody trying to listen online, I am sorry. My fault entirely. But we didn't get the good stuff yet. So hang on. Well, Kubernetes, right? Going back to the Kubernetes, which became ubiquitous. And another thing which is interesting in Kubernetes in relation to the databases is what Kubernetes was designed first for stateless applications, right? I mean, if you think about that in the early versions of Kubernetes, running database on Kubernetes would be oxymoron because, well, the database is where the state is, right? And the idea was, well, you know what, we'll have a database somewhere and that's where state will be kept so we can have our stateless applications in Kubernetes. But, you know, as if many things, they evolve. And people started to want to have a database on Kubernetes too, right? So you don't have to manage two different kinds of environments. And Kubernetes became much better in the recent years for handling those stateful applications such as databases. And you can see the Kubernetes operators, and that is kind of a way how you run their databases available for many most popular open source databases and not just them. What you also see is recognition of that effort in their community. Right? Many of you probably heard about, well, data on Kubernetes community, right, if you guys are here, which was going pretty strong. Like a few years ago, then Percona joined this effort where there are less than 100 of official members. Now it's more than 5,000. So there's like a lot of people interested not just into running that, but in actually participating in finding ways how to make it better. Okay. So what is interesting in this case, and this is kind of a stats from 2022. Unfortunately, I don't have a more recent report, right? What is interesting in this case, what we can see is what for a lot of companies participating in this community, we can see a lot of them are already running number of workloads on the Kubernetes, right? And we can see a lot of folks are expecting to increase that. What I think is also interesting in this case is how people think about that. Does that end up working for them? And what we see in this regard is what people moving workloads to Kubernetes or starting to run the data-intensive workloads in Kubernetes are pretty satisfied, right? As you can see, we kind of very satisfied or somewhat satisfied, right? As you typically get asked in the surveys. Here is now another little stats for you, right? If you need to, convince your boss to let you try running a database on Kubernetes. This is from CNCF, right? So this is not a data on Kubernetes people, also known as data on Kubernetes zealots, right? This is overall Kubernetes space, and what we can see in this case is open source monitoring, databases, messaging, right? These are some of the fastest growing workloads. What I think is interesting in this case, all of them are pretty much data intensive. Because even if I speak about open source monitoring, guess what, right? It's going to store and process a lot of observability data, so it kind of includes some sort of data store. Here is some more interesting stats, right, about their data-related technologies on Kubernetes, and we can see what, databases, right, I think which people mean in this case like operational databases, and analytics are very very common, right? And this is kind of what is % of respondents run different workloads on Kubernetes. Okay, now let's go about some specifics here, right? Hope I provide you some stats in terms of what is a good idea to, or why is it a good idea to run database on Kubernetes. Now, I mentioned the operators, right? What is exactly those like an operator concept I mentioned, and why is it important, right? Now, if somebody is responsible for database operations, making sure it runs healthy and so on, right? How do we call that person? Well, that is an operator, right, in many cases. Yeah, you can also call it like, DBA and whatever, right? And that is essentially that concept which is now translate to the software, right? The operator is the piece of code which is responsible for doing everything which needs to be done with databases. Now, why do we need that? Well, because if you think about your simple application deployment, let's say, hey, I want to deploy 10 copies of a stateless app server, right? Well, you just, deploy them in kind of any order. You can kill them at any time. It's kind of all like a very loose and easy. That is not how things work with databases, right? With databases, you have to practice kind of a certain care, right? If you are deploying the cluster, it has to be deployed in a particular order, right? If you want to, for example, perform the rolling upgrade, right, you need to, do that kind of carefully, right? Go ahead. So that second part also didn't work, right? Is it? What's that? You're good. You good? You were getting audio out of here. You are now. Oh, I see. So I have to say, oh, the speakers didn't work. Oh, that's the speaker didn't work. But it worked for our esteemed recorded audience. Okay, that's good. I thought I have to like say sorry for a second time, right? So it finally gets to people. Okay. Oh, okay. You just like playing the flights. Okay. Yes. Yes, my kids also did that like 10 years ago. Okay, back to Kubernetes operators, right? So with databases, you have to have a certain care, right? So there is a lot of logic in terms of managing databases appropriately, right? Like upgrades, backups, scaling up, down, wherever, right? That is what would be done, manually by a human operator, now can be coded in that operator concept, right? Now, when you talk about the databases, right, we often talk, and many applications in general, right, we often talk about day one and day two, right? Your day one is saying, hey, I have an installation and initial configuration, right? And then day two is the rest, right? The rest of a database life, right? That's where we have to make sure backups, scaling, self-healing, upgrades, and so on and so forth, right? And what is very interesting with databases is they spend vast majority of their life in that kind of day two, right? With databases, we cannot generally say, well, you know what, if it's kind of sufficiently fucked up, just we wipe it off, right, and start from scratch, as we often can do with applications, right? Those days, just, they deploy the clean code from scratch instead of trying to kind of, modify it is very common approach those days, right? And that is what the operators are very good at. And that is where I would say like an other approach is to deploy the database on Kubernetes. Just you can take the MySQL Docker container, right, and throw it into Kubernetes. Well, you can do that, right, and that simplifies your kind of day one thing, but that is not really useful for day two. That is where most of the production databases spend vast majority of their life. Now, at Percona, we have built Kubernetes operators, right, and we've been doing that for a while. Like our MySQL operator, for example, was released as GA years before Oracle came to release them. And I have made a little kind of tutorial for those who don't have a lot of experience with Kubernetes to show you, right, what exactly you can do with it, right? And you may be pleasantly surprised as how easy it is to do many things with Kubernetes operators compared to what it would take to deploy, manage, scale, execute backups, right, on the conventional cluster builds on VM. What also is interesting, and why you can see what this Kubernetes database on Kubernetes approach winning a lot of hearts and minds, is what there is a lot of database as a service solutions which have been built recently are actually built using Kubernetes as a backend. Right, like this is just example of a number of folks who use Kubernetes backend, right, and they typically use either open source, right, or maybe some sort of like a proprietary operators to do that, right? So that tells me two things, right? If they're doing that, well, that means it kind of works, right? If they would be totally kind of blowing up their customer databases, right? You probably would hear about that, right? And B, that is reasonably efficient, right? Because obviously if it would be like 10 times slower than running databases on VMs, that would be a problem, right? And I think that is important point is what we see with the recent state of Kubernetes, right? The performance overhead from Kubernetes compared to the same, let's say VMs, is actually quite minimal. Okay, let's now go to talk about specific practices. Now, what I would encourage you also is to be active. If you violently disagree with something, so just say like, Peter, this is wrong, right? And that will be helpful. Probably can do a better presentation next time. The first one is something I already mentioned to you. Use operators, right? When you're looking at the different options to deploy the database you plan to run on database, look for the good, full features, stable operators out there and use them rather than other deployment time. Then second one, which is very important, is set up for high availability, right? Of course, if you care about that in production. An important reason for that is they're relying on a single instance in Kubernetes is totally not a good idea, right? Like, I mean, if you are, I've seen a number of people just saying, hey, you know what, we deploy the single instance and, on VM or in bare metal and it actually works and you didn't have a problem for years. Well, remember, Kubernetes was designed with the idea of treat your nodes as cattle, not pets, right? So if if one of them dies, right, it's not like particular thing to shed the tear about, right? But if you only have a single node where the database runs, that can be the problem. The second thing, which is also very important here, is what you want your data to be persistent, right? And that means, in Kubernetes, the concept is different compared to your kind of like a VM, right? When a sort of like, or like especially like a physical box. You have a hard drive, right? Until you wipe them off, right? The data stays there, right? In case of Kubernetes, is designed for stateless stuff, so unless you specifically stated what I want to keep that state, right, on the persistent volumes, right, it will disappear, right, when that container is killed, right? Now, for persistent volumes, you can use both the local disks, right, or fast remote storage, right? And obviously, we have different properties, right? If you use something like EBS, it has a certain level of redundancy built into that, but it's also rather expensive, right, and also rather slow. Like here is an interesting image I grabbed from one of well, actually our guys presenting comparison between NVMe local storage and their provisioned IO storage, right, which is another way to get a good performance if IO-bound workloads. And what we can see here is what, even if we are getting like a lot slower, like this kind of like a 10 times slower in number of IOPS storage, still costs us like almost 10 times as much, right, in this case, compared to NVMe. So if you use the local NVMe, yes, it is non-redundant, and that means in this case you want to make sure you have like a replication on a database level, well, which you often do anyway, right? But it's much more performant and you know, cost effective. Next thing is keep data per pod relatively small. Right? I think this is interesting because if you look at sort of like a conventional database setup, databases often like this kind of like a big iron, right? And people may say, well, I have this kind of like a monster server with a lot of storage, right? And I run my single Oracle, Postgres, MySQL, doesn't matter, instance on it, right, which has, you know, like 50 terabyte of storage, right, or whatever that number is. Well, that is probably not going to be very good in Kubernetes environment, right? And what that means, often, look, not every database is very good for to move to Kubernetes, right? In certain cases, like a very large databases, people may not have a very very good success with just yet, right? Unless they've been moved to you know, distributed database, right, which you kind of designed more to that smaller nodes. What is also so that is not a good idea. The other thing I would consider is thinking about like appropriate node sizes. And what is interesting in this regard is when you look at application deployments, right, your normal app server, web server, proxy, whatever, right? Often you don't particularly need the big boxes, right? And what I have seen a lot of Kubernetes clusters out there may be engineered with relatively small node sizes, right? And then you come and say, well, I want to run the database on Kubernetes. Well, and guess what? In this regard, you need probably much larger nodes, right? So the shape of your Kubernetes cluster configuration may be different, right? If you are looking to move like a 64 core node, right, in Kubernetes, well, guess what, right? You need to make sure the nodes underneath your Kubernetes cluster have at least that amount. Okay. Second, thing number 6 is to configure resources in requests and limits. So what are those things? Well, if you think about if you just have the Kubernetes pod deployed with no kind of hints about how much resources it needs, it will be scheduled somewhere, and it will be able to utilize all the CPU resources, but will not have any guarantees in terms of how many resources it will get. In certain cases, it is not bad, right? For example, in development environment, you may say, hey, look, I just want to use as many resources as possible, but you know what, if a lot of guys are using the system right now, right, and I kind of get less performance, that is okay, right? Now, in production environment, we typically want a different, right? We want to make sure is what the database performance is predictable, right? Otherwise, it kind of becomes rather hard to work, right? And in this case, you want to make sure you're configuring that, and then often for CPU, we set requests and limits to the same number, right? So it works kind of in this regard similar to VM, right? Because if you provision VM, you allocate kind of 4 CPU cores to that, right? And you're not using some sort of like overcommitting. Well, you are guaranteed those 4 CPU cores will be dedicated for that VM, and you're not going to get more, right? But you're not going to get less, right? So here is, let's say, like a free concept of what you can use. Like one is a shared resources, right? Is which is quite usable for development environment. Then you can have request limits, right, in a certain certain shape, right, which you can do. The danger we want to highlight here, right, is if you have I don't know, let's say 8 core boxes, right, and then you allocate like a 6, let's say, CPU cores, right, to the database resources. Well, guess what, right? Only one of them can be scheduled to the physical node, right, a virtual node, right, and you will waste. So in this regard, with the databases, we often kind of want to emulate that, I would say, their VM-like environment, right, where you have like a single sort of like a database pod runs on a single VM. And in this case, we want to essentially keep the limits pretty close to the allocatable mode, right? Or if you say, hey, you know, I want to have 2 of them, then, you know, we also want to make sure they kind of fit nicely, not allocating a lot of space, a lot of, you know, waste. Okay, next thing, use proper anti-affinity, right? What is anti-affinity? Well, let's say I have a 3-node database cluster, right, which I want to be reliable. Well, I want those 3 nodes to be on a different physical servers, right? Even if I kind of chopped in a number of kind of different VMs, right, underneath, right? Well, maybe I even want them to be like in a different physical racks, right? So that is how you can specify the affinity rules to where to make sure you don't have all your eggs in that basket, right? And that again depends on your requirement in the cloud. You would often say, hey, you know, if you am looking to have a very reliable cluster, I would use a concept of availability zone, right, and make a different nodes in a different availability zones. Next one is wherever database is, Kubernetes doesn't make it magical. You know, some operators may apply their kind of own, you know, tuning compared to what like a stock, you know, like a Linux package may provide. But in generally, still, you need to tune your database for optimal results, right? So indexes, especially queries, right? You still need to take care of them as usual, right? I think for most of you guys that goes without saying, but I've seen a lot of kind of junior developers, when we speak like some next generation of technology, they kind of expect magic. Finally, I don't have to learn about all this kind of a pesky database internals, right? And then it will just do everything automatically for me. Well, perhaps some things, but not everything, right? Like one of the tools you can consider for that would be PM. That is an open source software tool for Percona, which has a lot of deep insights for MySQL, MongoDB, Postgres to help you with tuning settings, queries, and so on and so forth. Next one is, it's a very good idea to also to understand the database you're using, what kind of options does it have to scale. Some databases, distributed databases, right, they can help you to scale both reads and writes, right? And a lot of, I would say, databases which are designed for the cloud in the last few years, right, they are, or like probably like the decade by now, these tend to be distributed databases, right? Things like MySQL, Postgres, right, they have been designed many decades ago by now, right, and they sort of like, they're designed for a single node and then added like a kind of like some clustering, sharding, right, as an afterthought, right? So in this case, if you are thinking about what database can scale out, right? Well, we have like a TiDB, for example, right? Do we have anybody from TiDB here? Oh, look at that. We have a bunch of folks from TiDB, right? So if you want to talk about TiDB, come to them. And also PlanetScale, right? Yes. The source survival of a PlanetScale is here. Great, right. Any other distributed databases? What? Yugabyte. Yes, yeah. Yes, yeah, Yugabyte. Right now, yes, yeah, that's right. That's another cool operational distributed database. So yes, if you are running one of those databases or other distributed databases, guess what? You can scale number of loads and scale read and writes, right? In other cases, if you are running MySQL like Postgres, right? Well, you often would be limited if you need to scale writes, right? You need kind of to scale up, go to larger loads, provision more IOPS, right? If you want to scale reads, well, you probably can have read replicas, right? And well, for non-relational databases, MongoDBs, Cassandras, right? They typically also have some sort of sharding setup. But again, the point here, right, is to understand how to scale your database so you don't really have wrong assumptions, saying, oh, well, you know what, I now started with one node, but if I grow my database to 50 terabytes, I just going to, run it as a magically distributed database. Maybe not. Also, control eviction priority, right? Well, Kubernetes is something which evicts can evict some of the nodes, right? Like in this case, for various reasons, right? And the database nodes are not are expensive to do that, right? When you're starting database node, often it would have to do like some, crash recovery if you just killed it, right? Even if it doesn't have to do that and it will shut down properly, often it will take warm up to fill all the buffers, right? Caches, right? So with database, you don't want Kubernetes to do what it likes to do, right? And mess around all the time, right? Yes, sometimes you want to invoke the pod and reallocate that, but you want to tune priorities. Well, exposing the database, that is not an important thing, right? You want to make sure from security standpoint, you only expose your database outside of that Kubernetes cluster if you need to. A lot of bad security incidents happens and people expose, let's say, database outside of their secure environment, because they just want to much more conveniently access it from somewhere, right? And then bad things happen. Kubernetes is the same. Encryption. Data at rest, data in transit, you want that encrypted. The good thing about encryption, or misconception about encryption, right? Encryption those days is pretty cheap. Like a modern CPUs, right? They have like a special encryption instructions to encrypt the data very quickly, very efficiently, right? That also applies to to TLS data in encryption, right? So you typically just want to make sure you use that for extra security, right? And that's typically much better and safer option than kind of just saying, oh, I need to encrypt this data, not that data. This connection can go unencrypted, right? Because mistakes can be very costly, and savings from not doing encryption are relatively small. Also, another security things, the Kubernetes has a pretty good built-in concept as a Kubernetes secrets. It's a very good way to pass the database access credentials to your application, right? Instead of, you know, committing it or keeping it in the source code, right? And so on and so forth, right? Again, like a very good practice, right? And you can look at the operators which also support, you know, integration with Kubernetes secrets for things they use. Backups. We spoke about clustering and what you need to have ability in Kubernetes clusters, but hey, it does not eliminate the need for backups, which you want to make sure you set up. As we said, keep them off a node, off a cluster. We have majority of folks keeping backups in, you know, S3 compatible storage, right, or some other object store works pretty well. Now, I already flagged some of the folks here, like Vitess, /PlanetScale, Neon, Yugabyte, TiDB, right? I think these are all pretty cool databases to consider, because they have been all designed with this kind of new, you know, cloud-native world in mind, compared to their MySQL and Postgres, which are fantastic databases, but let's face it, they have been designed for a different world, right? And they have been just, you know, adapting for what is the new solutions can provide. Number 16 is consider CPU choices if you have efficiently. In particular, I think if you are on Amazon, look at Graviton ARM CPUs. They are, you know, pretty efficient and you know, relatively power efficient. And we think there's like there's a lot of development, you know, going on out there. Number 17, what I would mention is pick what exactly Kubernetes deployment is right for you, right? Because I have seen different teams, some of them saying, oh my gosh, managing Kubernetes, no, we don't want to do that. That's kind of another load on that. In this case, you can provide, use like a managed Kubernetes solutions, right, which are available now from a variety of clouds, right? Again, they would not eliminate you to know the Kubernetes, of course, to use it, but can reduce some of the toil which comes with the Kubernetes management, right? And maybe you know, provide some, you know, cool automatic you know, additions. Like, hey, if you deploy the manage Kubernetes on AWS, you can say, hey, you know, manage the scale of my Kubernetes environment automatically, right? If I need more resources, you can scale Kubernetes cluster automatically, right? Which can be very cool. Other folks, they like not manage Kubernetes, but deploy Kubernetes on VM. That has other benefits, right? If you say, hey, you know, I have this particular kind of blueprint, how we deploy Kubernetes, what Kubernetes version, and you want that to be the same on Amazon, Google, and on-prem, then, you know, using some of Kubernetes distributions, right, and just deploying it in different places may be a better choice for you. Number 18, you want also to make sure you monitor the utilization, right? Monitor utilization of your nodes, right? Because it is very easy in a Kubernetes space, right, to leave a lot of resources, right, which may not be even only used, but which may be not even kind of allocated for possible use. Like in that picture I showed you, right? Hey, you know what? We have nodes, right? And they just have some sort of slacks which cannot be possible allocated based on how things are configured, right? So that is a very important thing to save cost. Now, also, I think as you are looking at Kubernetes environment, right, and databases deployed out there, a lot of them are going to be kind of much more complicated, right? And also, as you, if you are kind of deploying, let's say, Linux package, you typically have some idea what it installs. Like, oh, I install MySQL, well, I'll have, let's say, MySQL process running. If you install the operator, right, even that's kind of operator from Percona, you probably would not have an idea what it installs completely, right, because it will install, you know, some proxy for load management, and then there's going to be, you know, some other bits and pieces, right? And I think that is where it's important to have some tools, right, so you can get that overall picture, what runs, right, and what, you know, talks to each other, right? There are a number of tools for that. One of the tools, which, well, I'm kind of helping with this open source project, right? It's called Karoot, right, which is quite helpful in automatically identifying what runs on Kubernetes cluster using kind of eBPF, right? So it doesn't rely on you installing any kind of additional agent, right? And that is how you can, right, discover what you actually get when you deploy some sort of operator, you know, and how those things talk to each other, and also if there are some problems, you can also see where they come from you. Okay, with that, let me ask you a question. So I went through my tips, and probably some of you, our Kubernetes experts, are sitting right now and thinking, oh, Peter, you forgot this very important thing. You know, any ideas? Anything I forgot? Anything you find a very important best practice? Yes?
You mentioned the storage choices,
Mm-hmm.
local NVMe for the node.
Yeah.
But survivability of your storage is the most important thing.
Oh, absolutely.
So ensuring that you have survivable storage in the form of volume or something, and also ensure your operator doesn't destroy the volume. Because operators are made by various people.
Yes.
Even you guys distribute some, maybe Mongo, the operator MongoDB publishes their own. So you have to investigate it. You can't just adopt it and say, okay.
Oh, yeah, absolutely, right? I think that is an interesting thing, right? Because the data is kind of like so easy to destroy in Kubernetes environment, you want to make sure it's very careful. Now, what I said, and maybe I wasn't clear about the NVMe, right, is, well, of course, you cannot rely on a single NVMe storage, right? But what often happens is when you would deploy, I don't know, let's say Postgres, you wouldn't deploy a single node, right? You would deploy the replicated cluster, right, with 3 nodes or something, right? Like in this case as well. Or of course, each of them would have its local NVMe storage, right? And yes, that storage may go down and kill the node, right? But there would be redundancy because of, you know, 2 other nodes, right? What will you get with somebody like EBS, right? You essentially have, you know, 3 nodes. Each of them has like data, you know, like wherever, copied so many, wherever many times, right? EBS copies that internally, right? So that is what we are talking about.
And that is exactly what I'm worried about, which is that if you use node local storage,
Yeah.
the destruction of a cluster automatically implies destruction of all of them, whereas volumes or mapping to EBS give you a different layer of survivability.
Yes. Yes, yeah. Well, and you know, I would say it's also like never say never, right? I would say like in certain cases, yes, like you may your workload may not be even IO bound, right? Like to begin with, right? Then that's a less of a problem. Okay.
I'd like to know your best practices for doing major upgrades. Like say
Well, I mean, if you look at the upgrades, right? I think Atlas Cloud is actually very nice because you can kind of expand, right, and then shrink environment. So what we like in this case is saying, hey, if I'm doing kind of like a minor upgrade, then typically operators can just, you know, run it together, right? In the cluster, it's kind of low risk, all good, right? If you have some major upgrade, it's often good to just, you know, you provision the new cluster, you kind of set up replication, ensure kind of everything works, right? And then you can do a cutoff, right? So this kind of like an approach. Okay. Yes. Yes. Yeah.
Yeah. What have you seen with Kubernetes installations that you've worked on? Do you see people doing special purpose Kubernetes cluster, or do they do just like an everything cluster and then figure it all out? Or?
Yeah, I think that is a good idea, right? We see a mix, right? In a number of cases, you see people having like a special purpose database cluster because the shape, right, what we see for the database nodes, right, they need can be different, right, what is optimal for applications. Yeah.
So for storage, you mentioned that before. So for things like portworx and special case storage that's built for Kubernetes, what's your opinion on things like that versus what other options are there for using things like caching and that sort of smarts and having the storage be a little more intelligent in the environment?
Yeah, well, look, I wouldn't, I know there's a lot of innovation, right, which goes in terms of storage, right? With that, we typically work with what, you know, customers have. Okay.
I don't think you mentioned anything about caching in this presentation. I know that caching is just generally a database thing, but I think you definitely want to.
Oh, yeah. No, absolutely. Well, I didn't mention caching, right? And I think there's a lot of tools coming out for that because it's not like really very Kubernetes related. But yes, I mean, I think if you look at this case, you have, you know, a number of caching solutions, right, which can be quite database specific. Okay, folks. Now, contrary to a popular belief, that is not the end of the presentation. I just wanted to take a brief pause, and now I'll get to like a next stage and talk about in a few minutes of what is coming, right? One is what you can do beyond Kubernetes operators, right? One thing what we see is for people who are using something like an RDS and saying, yes, you know what, it's all kind of good and fantastic, but you know what, having this kind of YAML files, which you do kind of, you know, kube apply, is not like that UX we got used to, right? I want something I can use my click ops skills, right, and deploy the database in a few clicks, right? And that is, I think, is quite important for certain users. We at Percona are also building the open source product for that called Percona Everest, which is currently in beta. And I would encourage you to try it out, maybe give us some feedback or maybe even kind of some code so we can make it better. Finally, wanted to highlight about a couple of things which I think coming in the future, right, and which are important. We are working on that stuff. I know like some other people working in this environment, and some things are kind of, you know, maybe working. One, which is an interesting challenge, is deploying databases across the Kubernetes clusters, right? We see a lot of people saying, hey, you know what? I don't believe in single Kubernetes cluster, right, as something which is kind of universally available, right? I want to make sure I survive the full Kubernetes cluster failure. And then there are some, you know, solutions coming up. Like, for example, this one is getting a lot of traction recently. There is some others as well. We at Percona operators, for example, we do support replication between, right? Many of our customers would have like a node or a cluster in a different Kubernetes cluster for disaster recovery, but there is no kind of single easy of orchestration multi-cluster just yet. Another thing, which is very easy, but I think very nice is their work going with automating automatic volume extension, right? Because what databases, they kind of intend to grow, right? And often what you want is saying, hey, I would want a Kubernetes operator to start with at, I don't know, say 10 gigabyte or whatever volume, if that's, EBS, right? And then grow it as needed to be larger, similar to what like RDS and similar technologies need to do, right? And I think what is fantastic in this case is what we are getting the appropriate universal support in Kubernetes for that interfaces, right? With the cloud vendors, right, or other storage vendors, which can provide that storage thing, right? And I think that is very important with the storage innovation that we are getting more and more with that, like a container storage interface, right, as interface to those advanced features, but in a universal way. So we don't have to, code specifically for, I don't know, some storage. After scaling, obviously that is another very much, wanted by some people. How can we make sure we can transparently scale our databases, up and down? That's what we see in the cloud, right, and number of options, right. And I think a related kind of trend of after scaling would be also after suspend for development, right? When I can say, hey, I deploy a database, I use it only every so often for development. Why can't it just automatically shut down, right, if it's inactive a certain amount of time, and when I'm kind of trying to connect to that, just bring it up in the background, right, so I don't have to think about managing and kind of spinning up and down that node myself. So that is another thing which I know like many people have been thinking about. Finally, ease of migration, right? Everybody, like wherever you introduce the new technologies, right, so you want to make sure it's easy to migrate, right? And that is something what we see there. Operator building various tools, right? Saying, hey, you know what? You can seed your database maybe from a backup you taken from the database which was not running Kubernetes. You take it on a S3, right, and initialize your cluster from that backup, or having something like as a rolling transition. And you can say, well, you can have a cluster. You can start some nodes in that which are in Kubernetes, right, until you finally migrate there completely, right? So various kind of approaches how to make the migration both easy and also not impacting production if a downtime, right, or something is a lot of work, very a lot of work going on. Well, with that, that's all I had, and I think I have a couple of more minutes for questions if you have any. Well, so if you think about like the suspend, in many cases, the idea in this case is this, right? I mean, if you look at a lot of classical databases, we don't have like a quite separation of a storage and compute, right? So what you'd have is some sort of a proxy, and the proxy knows, right, oh, if connection comes and I don't have any backend because the backend is out, I can bring up that backend and then transfer connection to it, right? That's one approach, right? If you look at like some of, I would say, like a new generation database, like Neon, they can have a separation of a storage or compute, right? So that out there kind of happens more after magically, right? In this case, because you can essentially spin up the or reuse the compute, right, in a very quick way. Okay. Oh yeah, I think you're next speaker. No. Who's next speaker? You are. Oh, okay. Yeah. And you started in 11, right? No. 11:15. Oh, okay. That's yes. Good. 12 more minutes. Okay. Well, then, thank you, folks.
That was a good presentation. Don't let the technical difficulties get you
Oh, don't worry about that. That's
It's off. One sound check, sound check. How do you work? Probably I need to go here. One, two. Yeah, should be all right. How's it going so far? That's the second.
Alrighty, everyone. We are ready for our next talk, which is using Kubernetes with distributed SQL databases. Please get settled up for the next talk. Alrighty. David Magda, everybody.
Sound check. You want to try this one? This is a good idea. It's something that Peter did not have. We're experimenting with the audio settings. Oh, man, no, I need your help. You see, no, it's hard.
There you go.
1, 1, 2, 2, 1, 2, 3. Hello, everyone. Take your seat. What? Disappeared? No, we don't need screen. Yeah, I'll be just standing and talking, and you'll be trying to figure out what I'm talking about. Let's do this reset, hard reset. Hopefully, my laptop will not fail me. I don't know what's happening. Probably we should check this one. Because when did it disappear? It was on, right? A minute ago. Yeah. It was on. Displays. My laptop can see it. What if I do stop mirroring? And then I do no, the laptop sees it. Source HDMI.
I think this one was
Huh? No signal? Yeah, I'm plugging it back. It gets the signal and my Mac sees it. Huh? You want to reset it? It is. But right now, the etcd community is not growing. It's not thriving. There are a few maintainers that have their primary jobs and they need to also to look after etcd. And sometimes it takes a lot of time to not just to introduce new features and capabilities to etcd, but just to do that basic maintenance work that is needed for Kubernetes, for other projects. So those are at least two reasons that I am aware of. There might be some other reasons. Because eventually, the Kubernetes community created a project that is called Kine. And Kine, what Kine does, it's a translation layer. Translation layer between Kubernetes and relational database. What it does, why is it necessary? Let's say that you belong to one of those companies that found the reason to replace etcd with some other database, like relational database. And Kubernetes itself, it does not support other databases by definition. So if you want to replace etcd, you need to use some translation layer. For instance, if you use Kine, and Kine is one of those well-known community projects, you still will have Kubernetes. And Kubernetes will continue using etcd APIs. So like whenever you deploy any part, your service or deployment in Kubernetes, Kubernetes will be calling using etcd API trying to talk to its etcd database. But if etcd is not there, then Kine will be intercepting those etcd calls, and Kine then can route those calls and use, let's say, Postgres or MySQL instead of SQLite. So this is what etcd does. It basically intercepts all those API calls from Kubernetes, and then it can actually use Postgres, MySQL, or another relational database as a meta store. And then throughout the presentation, you will see how you'll get to the distributed database. Because next, that's the agenda. That's the quick introduction to you, why we need this conversation and how we are going to achieve the Kubernetes deployment on a distributed SQL database. What's coming next? Right now, we are switching to another tab in my terminal window, and we'll deploy first Kubernetes on PostgreSQL. So Kubernetes will be using Postgres as its own meta store. And after that, we will do one extra step. We will deploy Kubernetes on a multi-region distributed PostgreSQL version, Yuga ByteDB. So Kubernetes, like Postgres, as Peter was saying, it's a database that was designed for single server deployments. However, these days, usually, you want to have something that is scalable and highly available, and Postgres ecosystem has many solutions. One of those solutions is Yuga ByteDB. I'm talking about Yuga ByteDB because the company pays me, because I'm bullish about Postgres, and I believe in Yuga ByteDB, all right? Take whatever explanation you like most. But generally speaking, for me as a developer, it's much easier just to use Yuga ByteDB because even though it's distributed, for me as an application developer, it's just one connection string to my database, and I don't care like how the data is sharded, distributed, how the fault tolerance works. I don't care. For me, it's just one database connection, same as with Postgres or MySQL. All right, let's do this. So what I'm using today, I'm using my laptop, but also I deployed 3 VMs in the United States West Coast. So I have a virtual machine running here, West 2, that's Los Angeles. Then we have another virtual machine in Oregon, West 1, and West 3 is Salt Lake City. I'm already connected to West 2. Yeah, I think, let me come here. Yeah, that's my machine on West 2. It's here somewhere in Los Angeles. And I will be using this machine to deploy my Kubernetes instance. And then also I already have on this machine Postgres running. So remember, the first step is let's deploy Kubernetes on Postgres and see how it works. Yeah, let me connect to, actually, I will connect to this instance from this window. And to connect to Postgres, Postgres actually comes pre-installed with Ubuntu. And I will connect to Postgres this way. I am using PSQL. I am connecting as a Postgres user. I'm connected, and here, as you can see, that my database is empty. I don't have any tables. I don't have any data. So now I want to start Kine. So Kine, if you Google for Kine, you will find this GitHub project. It's part of the K3S. This is the lightweight version of the Kubernetes. And here is, take a look at this extensive documentation. But at least it's straight to the point. Kine is the translation layer that allows you to use Kubernetes with SQLite, Postgres, MySQL, or Nets. I don't know what Nets is, but hopefully some of you know. How do we deploy it? Let's actually start with Kine first. Before we deploy Kubernetes with Kine over Postgres, we can do this. I need to go to my local folder because I have already cloned Kine. I'm here. And the next step is, it's written in Go. I'm starting Kine, and I'm asking Kine to connect to the following endpoint. And the beginning is the backend, because Kine supports several relational databases. I'm using Postgres, and this is going to be a hint to Kine that, hey, please start and use the Postgres backend implementation. And then where is my Postgres? That's my Postgres username and password. And that's my Postgres instance. It runs local on the same machine. Okay, and I'm connecting to the Postgres database. Let's start it. It still works. And it said that the Kine is available. Remember, here is I'm connected to my Postgres instance, and if I check the relations right now, here is you can see that Kine successfully connected to my Postgres database running locally and created these 2 tables. You actually have just one table that stores all the metadata that is being generated by Kubernetes, and also you have the sequence. The database sequence basically generates IDs for the events, because every event that is created and generated by Kubernetes, whether you deploy service, deployment, or whatever, it has a unique identifier, and the Kine generates those identifiers with the database. If you take a look at the structure of this Kine table, it's not, there is no any rocket science. You have this event ID, name of the event, when it was created, deleted in different revisions. And also, there are many indexes that were created to expedite some of the queries. Okay. So, for instance, let's take a look at this. I can select ID name from kind table. And let's get the last three. Yeah, we have only just 2 events. So when kind started, it decided to write down a few events into this table. So that's it. That's fine. But now, that's how it works, but it's not Kubernetes yet. So how do we start kind with Kubernetes? Let me do this. I want to drop this table for now. Let's do drop cascade, because I will be restarting kind with drop table kind cascade. It's empty again. For Kubernetes, when you use, if you check this documentation, it said that you can certainly run kind as a standalone process nearby your standard Kubernetes deployment. But today, for the sake of simplicity, I want to use lightweight version of Kubernetes. It's called by K3s. Anybody uses K3s actually? Yeah? Then it's going to be like speaking your own language today. So K3s, a quick intro for those of you who don't know, it's basically that's a minimalistic version of Kubernetes. And what's valuable for today's conversation is that take a look at this component. It comes kind comes prepackaged with K3s, which means that I can just start K3s, pass information about my data endpoint, and then everything is going to work fine. At least I hope so. It used to work for me in the past. Let's deploy it. How do we deploy? So what I will do, I will use curl. I will connect to this web address, and I will download a special installation script. This is actually one of the installation instructions for K3s. And then I will start K3s in the server configuration. I'm passing some essential settings. That's not the secret token. You need to use something more advanced. But this is what is interesting for us today, data store endpoint. And here is I'm passing this configuration. This endpoint looks exactly the same as the one we used for our just standalone kind deployment. And basically what will happen when I will deploy this Kubernetes instance on my local machine, then this endpoint will be passed, and Kubernetes will see that, yeah, the user wants to use Postgres, which means that I need to go to kind, and kind eventually will connect to my Postgres instance. Let's start it. Yeah, it downloads something, yeah, creates, and now it's starting K3s. We already have these 2 tables, and what I want to do now, yeah, it's started, meaning it will be running as a daemon on my operating system. And now, if you check this ID and name, from kind, right? We want to get from kind. Let's order by ID descending. We want to see the latest events generated by Kubernetes first, and then how about printing the last 3? You can see that, take a look at this number. Kubernetes was started barely a minute ago and already generated almost like 600 events. Like, it's a stateful system. It like runs silent. It just runs silently, but it always does something. And I don't have anything deployed. If I do this right now, and this number will keep growing. For instance, I will use this watch operator of PSQL, and I will keep executing this select every 2 seconds, and we will see that, yeah, something is happening. Something is being registered. I don't know, probably some heartbeats or whatever. I'm not a Kubernetes expert here. If you take a look at this, let's use kubectl, get nodes. We have it running. It's running. It's ready. It runs on my machine. So this is how easy it is to deploy Kubernetes on Postgres. And so right now, Postgres is used as your store. But there is one problem with Postgres when you compare it to etcd. etcd is highly available and highly scalable and highly available. Postgres by default, no. Postgres is like single server instance, and if Postgres, you can deploy Kubernetes across multiple servers, across multiple availability zones. That's probably what you want to do, because if Kubernetes goes down, you don't want the control plane to go down. But Postgres, you need to find some high availability solution. And as I said, there are many options. not many, but several options in the Postgres ecosystem that will help you to make Postgres scalable and highly available. They are just not built in the core Postgres. And let's use Yuga by DB. So today we will use Yuga by DB in this way. Let me first, what I will do, I will just destroy and stop the just created Kubernetes version. I no longer have this K3s installed. If I execute this command right now, you'll see that no, Kubernetes is not found. And here is where we'll see that Postgres no longer gets any events from Kubernetes because I stopped it. Let me just drop the tables. Yeah, I no longer need Postgres. Speaking about Yuga by DB, we will start introduction to Yuga by DB with the following command. And then I will explain you a little bit more. So again, I will be using curl to download the same installation script of K3s, of our lightweight version of Kubernetes. And then for the data store endpoint, I'm telling, please, when you start, use Postgres backend, the Postgres implementation of kind. But this time you will be connecting to the following Postgres instance. And here is, that's not Postgres instance, that's the Yuga by DB instance. I am using not the strongest password in the world, but that's my database endpoint. And this IP address is here. It's the same virtual machine. And I am deploying a multi-node Yuga by DB cluster. Let me actually show you that multi-node Yuga by DB cluster, because one of the instances is running locally. Yuga by DB exists in several versions. I mean, like you can, it's an open source project like Postgres. You can download and install and use it and don't pay any penny, or you can consume it as a cloud native, fully managed database. It's up to you. I have this Yuga by D tool, and I want to check the status of my database, and I know that I store the data, the configuration of the cluster in the following local directory, so I can go to this directory and get the information, Yuga by D, no, it needs to be this way. So what I have a 3-node cluster running, it's available, and I can connect to it. What we will be doing right now, let me use PSQL. I want to connect to my Yuga by DB instance, to this one. The port number is this one, and the user is Yuga by. I'm connected to Yuga by DB, and as long as Yuga by DB is distributed version of Postgres, it certainly supports the majority of tools and frameworks and libraries that we created for Postgres. PSQL is not an exception. I continue using PSQL. So I don't have any data in Yuga by DB in my distributed cluster. So now let me start Kubernetes on Yuga by DB. You will see that Kine also connected to Yuga by DB, and it already created the tables. What I want to do now, let me show you actually that Yuga by DB cluster and do a little bit more advanced intro for you. Yuga by DB comes with this UI. So what I have, I'm running a 3-node cluster. And I'm running this cluster in a multi-region configuration, which means that I have one node of the database deployed here in Los Angeles, another one is in Oregon, and another one is in Salt Lake City. Why I do this? Probably I decided that I want to tolerate region-level outages. Region-level outages happen, and if, let's say, United States West 2 in Los Angeles goes down for any reason, my Kubernetes, if I also deploy Kubernetes in other regions like Kubernetes itself, right? During the demo I don't do this, then my database will be available, no any data loss, and I will be able to execute my application workloads. Also, when it comes to multi-region configurations with databases, you know that it's a distributed database. And by definition, distributed database nodes are interconnected through network. And you already take that network hit, right? The latency hit because the network. That's why, especially when you deploy across multiple regions, that network impact on the latency can be even higher, which means that when you deploy across multiple regions, you need to find one of the ways how you can minimize the latency impact. For my today's presentation, I decided to write, I want to define one of the preferred regions. Because by default, this is a distributed database. And when I have this kind table or any other application table that you create in the database, it will be sharded. Basically, your data will be split into shards, and all those data will be distributed across all of your nodes, and then you can load balance your reads and write requests. So this is how you utilize the entire cluster capacity. But for my, let's say, use case today, I'm telling, yeah, for the sake of high availability, I certainly want the copy of the data to be stored in all of the in all of the regions, but I want to define a preferred region. The region where nodes will be handling all the reads and writes by default. The primary copy of the data will be in one of those regions. So I selected United States West 2 as the preferred region, which means that Kine and Kubernetes, they will be executing quite advanced selects with multiple joins, et cetera, and by default, all of those requests will be handled by the database nodes that are deployed in my preferred region. I don't want those joins to span multiple regions, so that's what I did. And we have, this is the new UI that exists in Yuga by DB, but we have a little bit older one. I call it the veteran of Yugabyte. And it shows a little bit more advanced information. So that's my node in Los Angeles. And you see this leader preference priority. It means that this node belongs to the preferred region, meaning that by default, reads and writes will go to this node. If, let's say, the data center or region in the United States West 2 in Los Angeles goes down, then priority number 2, this node will become the next preferred one, all the nodes. And here is in this configuration, I'm running just 3-node cluster. You can deploy as many nodes as you like in every region. It's up to you. Okay, enough. Now, when you go back here, you can see that, yeah, Kubernetes has been studied successfully on Yuga by DB. Let's check it. How about we run the same request? I want to get the latest events that are being generated by Kubernetes. Order by ID descending, and let's print limit 3. And let's do watch. Please repeat this request for me. Yeah, the Kubernetes is up and running, and I can see that something is happening with the Kubernetes cluster. If I do this, let's do K3S cube CTL, get nodes. We have it, but we don't have any pods. We don't have anything else. And generally speaking, it's easy. You saw like it took us how many? Yeah, 30 minutes and probably 5 minutes for troubleshooting. 25 minutes to deploy Kubernetes, first on Postgres, and then to deploy Kubernetes on a distributed multi-region database. It's all straightforward. And we used Kine. It's something that is maintained and created by the Kubernetes community. But the question is what? How many of you are DevOps people who are responsible for running Kubernetes? Okay, how many of you are application developers who are deploying Kubernetes? Yeah. So generally for you, it's interesting to learn those insights, but let's say that eventually we want to deploy our stuff on Kubernetes. Let's try to deploy something on Kubernetes to make sure that this configuration eventually works. What I did, probably you can come up with a better sample, but I just Googled and I found some repository with Kubernetes sample applications, and I want to use them today. So I will use this command. I will deploy some emoji water example. Have anybody heard about this example? Me too, me neither, Andy. But at least let's try to deploy it right now. And now it's gonna be deployed, and here is, let's pay attention to, yeah, here as you can see that something is happening, and I stopped generating events. You can see that, yeah, voting, emoji water. So generally, you can see what's happening inside, right? We are deploying, we application developers deploying something on Kubernetes, and then this information is being stored in the meta store, and Kine intercepts those etcd API calls, and eventually all this data is stored to Yuga by DB, and it's replicated across multiple regions. So you're not losing this data even if one of your database nodes goes down and you have a meltdown in your region. Let's restart this. So now, if I do this, let's get information. So what was deployed? Yeah, we have several pods, yes, several microservices. Then we have services, deployments, and replica sets, pretty standard configuration. And this one is web. We can actually do an extra check. Let's say that my application was successfully deployed on the following Kubernetes configuration. But now let's make sure that the application itself responds. I know that I can connect to this endpoint and check that, yeah, we are good to go. Let's use HTTP get, and the port number is 80. Yeah, it's all good. So we've got some response from the application, HTML text. So that's how it works. That's it. That's it. It just works. And it's quite simple and quite straightforward. However, there was one final item on the agenda. Do we need to have any kind-specific optimizations for distributed SQL? Because you saw that today, I didn't do anything. I started Kubernetes using kind, and I use the kind version that you download from the upstream of the project. And basically, kind continues using the Postgres backend, but that Postgres backend works out of the box with the distributed version of Postgres. However, if to be brutally honest with you, a friend of mine, colleague Frank Pashuro, he sits here, half a year ago, sometimes we had that gig, when we want to find, let's say, some interesting, well-known application that is written for Postgres, and we want to check. All right. Probably it's no longer necessary. If you can try to troubleshoot, let's do it. Don't do that. Yeah. And we actually came across Kubernetes, we came across kind. And when we were deploying, a half a year ago, when we were deploying Kubernetes with kind on Yuga by DB, sometimes the deployment would fail, sometimes it would succeed. Why would it fail on some occasions? We decided to check. That was related to the SQL requests that were generated by kind. Kind internally has just one single table, but if you take a look at the logs or if you take a look at the implementation of the project, you will find that it just generates like those massive SQL requests that need to join the data. And sometimes during the startup of Kubernetes on kind, something would blow out and the Kubernetes would not start. And eventually, Frank and I, we forked kind and we just, just created indexes a little bit differently. We also enabled some of their optimizations for the distributed SQL databases. And our version and that version of kind and Kubernetes started working on Yuga by DB. Today, when I was recording for this presentation, that was no longer necessary. But does it mean that we can just go ahead and use the current version of kind? Probably yes, it's all to go. But there is one important lesson for us developers. When you're transitioning, let's say, from a relational database and your application, you already have some application that was written for the database, you created it. And even if the database, like Yuga by DB, that is Postgres compatible, it's feature and runtime compatible, it's pretty much highly likely that you will take your application, you will connect, and it all will work. Still, then run some load testing, run some performance testing, because you might discover that you need to optimize some of the requests, some of these workloads that were created for Postgres or MySQL before. So that's why distributed SQL is the same SQL that works like a charm. It allows you to scale beyond the capacity of a single server. It allows you to tolerate various outages because it's distributed, it runs across multiple nodes. But also as an application developer, your learning curve will be much, much shorter, because if you already know SQL, if you know how to use, if you're a Java developer, you use Hibernate, Spring Data, or you use some other ORM for your programming language, it's going to be an easy transition for you. But still, make sure you run some load testing and performance testing, because still you might want to optimize some of the requests as long as your database runs over the distributed environment. But speaking about Kubernetes, if we go to the original configuration, Kubernetes is great. It uses etcd by default. There are some of the use cases when etcd is not enough. It can be related to the scalability issues. Some of the companies have concerns about the state of the etcd community, but nevertheless, you might have some other reason. Keep in mind that the Kubernetes community has special project kind that allows you to replace etcd with another meta store, another database. It can be Postgres, it can be MySQL, it can be Yuga-DB, whatever you prefer. Or, and if you, let's say, eventually listen to the presentation of Peter, who kind of hinted and suggested that, guys, probably you can run questions. If you have questions, please ask. If not, enjoy lunch. Questions?
Going once, twice, thrice. All right. Thank you, David. Thank you for the amazing presentation. Thank you so much.
2 test. Does that work? Sure.
How do I pronounce it correctly? I don't want to mess this up.
Everyone, we'll be starting with our next talk titled MySQL Connections, Handling and Pooling by Matthias Cronville.
All right. Welcome, everyone. So, my name is Matthias Cronville. I am an enterprise customer engineer at SCaLE, still at SCaLE, which is good. I'll be talking today a bit about MySQL, high availability, how you can do connection handling, connection pooling, things like that. There will be time for questions at the end, so if you have questions, please save them for that. And with that, let's get started. So, people always ask me, like, is it MySQL or MySQL or whatever? So the official way to pronounce it is MySQL, but we're open for all other suggestions. This is from the manual. The link is there, so you can see. Today we're going to give a brief introduction about MySQL, how it came to be that I'm talking here about connections and connection pooling, because like life is short and why would you talk about connection pooling? Then some challenges about connection management. Then I'm going to go a little bit on how SCaLE supports connections, and then at the end we'll have time for questions. So, MySQL is still the top open source database. We're losing traction against Postgres, but looking at DB rankings, we're still the biggest one. So founded in 1995, a long time ago, 30 years next year. Now currently Oracle Corporation owns MySQL, and that's been the reason for many of the flame wars around there on the internet. So we'll see how that develops. And current release is still 8.0. That's the one you should be using in production. If you're using anything else, anything older, please upgrade. Anything newer, please be careful. In 2019, it won DBMS of the Year on DB rankings. And it's widely used by top websites in the world. Think Facebook, Twitter, Booking.com, all of those very large web applications are using MySQL. And this is also why connection handling and connection pooling is kind of important, because web traffic is very unpredictable. Like if you have an application, in-house application, you can pretty much predict how many users you'll have, because the amount of employees you have is probably going to be the maximum number of connections. But if you have a web application like Twitter and someone does something stupid or says something nice, you might experience a little spike in connections and traffic. So. Why did we get so popular? Mostly initially because it's free and open source software. It's very easy to install. Like my first job, we were using MySQL, and all the system engineers were doing was apt-get install MySQL server. Done. Works. If you grow a little bit, it becomes a little bit harder to install and to manage, but still can be done. And it's able to handle a lot of connections. Like if you would run Oracle database for the same amount of connections, it costs you an arm and a leg on licensing alone. So MySQL free. And it was very easy in the early days of PHP MySQL to set it up. Like PHP came by default with MySQL connectors enabled. Like if you want to use Postgres back in the day, you'd have to recompile your PHP with all the flags to support it and to be able to connect, which was a big pain in the egg. So that's why MySQL really gained a lot of popularity, and then finally also because replication, and we're going to go a little bit deeper there. So Replication is a way to have more copies of your data that you can actually use. It's like you would always have a single primary where you can write to, but you can have a lot of replicas, like there's 3 dots here, but you can't see those with the lighting. You can have a lot of replicas. There's 3 here, but you can have multiple. And so you can use all those replicas for reach scale out. So you can write to this one server, because most of the web traffic, like if you think about a website like booking.com, how many hotels do you browse before you book one? Like it's probably going to be a magnitude of that. So only the writes need to go there, but all the reads can go to the replicas. The replicas can also be used for high availability and failover. If something happens with your primary, you can say, okay, let's promote a replica to become the new primary and continue operations for like nothing happened. You can use the replicas for backups, like you don't have to take the primary down for backups, which is an easy thing to do. A few replication ways. Traditionally, replication was asynchronous. So that means that the primary executes your transaction and doesn't care about any of the replicas to be catching it up. So at commit time, it would write the transaction to a binary log, and then the replica would, at its own pace, read that binary log and apply it in its local data copy. In an ideal world, you keep that replication delay, like the replica behind your primary, under 1 second, but it can grow if the replica can't keep up. That's why semi-sync came to be. Like, we want to make sure that at least one replica had received the transaction before the primary would continue working, or continue committing the transaction. So you would have more safe, like crash safety, if your primary would crash and no replicas had the transaction received, it would have not been committed, and so it would not be acknowledged to the client. And then at the end, you have synchronous replication. It's virtually synchronous because it can still be behind, but in this case, the cluster solution that you would use would make sure that transactions are synchronized across the cluster, but not necessarily all applied there already. So now we come to the point where we talk about connection handling. So MySQL has a thread-based architecture as opposed to Postgres, where you have a process-based connection system. Like if you would look at a Linux server's process list on where it's running a Postgres server, you would see all the connections in the process list. While on MySQL, you would just see a MySQL process and no other processes. But if you then would go look into the threads, you would see one thread per connection that MySQL uses. So that's a good and a bad thing at the same time. Good thing is you have it fully isolated, and so the threads can work on their own pace. The bad thing is that you cannot do multi-threaded transactions. Like MySQL doesn't support that because of this architecture. So whenever you get a client that tries to connect to MySQL, it queues up its connection request in a queue here on the front, and then there's a receiver thread working inside of the server that handles the connection requests that are incoming, and it will see if there's a thread available in the thread cache, and if there is one, it will take one, it will assign that to the connection, and this is the thread that will handle that connection. If there's no thread available in the cache, it will create a new one, which is going to be a bit more expensive, but in modern systems, that's not so expensive anymore. In older systems, this was very important to have that thread cache, but nowadays it's not that big of a thing anymore. And then in the end here, this is going to be important. This is what's called a thread object. And that's assigned for each of the user threads. And that thread object is a one-to-one mapping with the thread of the user. And that basically holds all the memory that this thread will be using. And so we'll come back to that later, why that is an important thing. By default, and most common example there is PHP, connections are short-lived. So you connect to your database, you do your workload, and at the end you disconnect. That's how a short-lived connection works. So your client sends a query, sends multiple queries, gets results, but then at the end of the page it just disconnects. And at the disconnect phase, this thread object gets deallocated. So any memory that this thing got assigned will be freed by to the OS by the server. As opposed to long-lived connections, where these connections are actually kept indefinitely. And so this thread object also is kept indefinitely until the connection is actually closed or recycled. This thread object will be there and will be keeping memory. So if you have a large thread object, you can have a large number of memory and you can get OM issues with that. So in an ideal world, the threads just keep going forever. Unfortunately, CPU threads are still limited, like there's no unlimited number of threads that you can have. And so it's basically the OS that will decide when a thread gets time to spend on the CPU. Like it's the CPU's time shared. So they need to wait until it's their turn. Then there's a few things it can wait for, like mutexes is one of the important things in the database. Like if something has to make a change to the internal structures in the database, a mutex will be requested and hopefully at some point granted. So that means that during the wait for the mutex to be granted, the thread is actually blocked. And once the mutex is granted, other threads that will be waiting for that same mutex will be waiting on this thread to finish its work. So that's also one thing. And then another typical thing in database world is locking. It's important to be able to lock the records in the data when changes are being made, so you don't override each other's changes. There's data logs when you do insert, update, deletes. There's metadata logs when you need to do DDL changes like create, alter, drop. And then finally, there's also I/O things that you might have to wait for, like a disk is a typical example, but a network connection is also something you might want to wait for, have to wait for. Nowadays, with SSDs, disks are better, performance is better, but still there's a limited throughput to those, so it's always going to be a thing to consider. So, and then memory allocation is another challenge that we have already touched upon briefly. So the thread object holds per connection buffers. Short-lived connections can have a lot of overhead of allocating, deallocating memory, all of those things, but then long-lived connections can also have a big memory pressure. So if you have a lot of long-lived connections, then the memory hogging can grow, and you might run into memory issues there. And then finally, another challenge with connections is service discovery. So we've talked about replication, but you have to know where the primary is. So if your application needs to connect there, you have to know where it is. If you want to use the replicas for read scale out, you have to know which replicas are available, where they are, how to connect to them, all of those things. There's a few common techniques, like I've seen people using DNS records for making sure where the primary is, or a floating IP address like that you can move across different servers. For replicas, you can just load balance between a pool of replicas, but you have to also then need to monitor which replicas are lagging behind, which replicas are currently in use for like taking a backup, things like that. So that's also a big thing. So this is where connection pooling can definitely help. Connection pool is typically an application that's sitting in the middle between your application and your database, and it basically holds a number of connections. So if you're using Java, like a Tomcat server or Rails, that typically creates a number of connections when it starts up. And when your application then needs a database connection, it basically requests to the connection pool like, hey, I need a connection. Then the pool will say, hey, this is a connection I have available, or I will make a new connection for you. And basically, by doing connection pooling, you make a short-lived connection become a long-lived connection, because once your work is done, your application will return the connection to the pool and not disconnect. And the pool will then handle the things like, hey, do I need to recycle memory? Do I want to close this connection or not? That's all up to the pool. And sometimes, if you come from a PHP background like myself, connection pooling wasn't a real thing there back in the day. So you had to use an external application. And this is where proxy SQL as an application is something that's very useful. So what is proxy SQL? It's a high-performance proxy that sits between your MySQL database and your application. And it's designed from the ground up to speak the MySQL protocol. So it can provide load balancing between between the different servers, and it understands the topology. Like if you send a query and you say, I want this to go to a reader, then proxy SQL can know that from looking at the query or from whatever you tell it to. It knows whether an instance on the back end is up or down. It can be configured as a connection pooling application. So by default, proxy SQL will keep 10% of the connections to the back end alive. So if you don't make any other configurations and you just install proxy SQL, it will act as a connection pool on its own. And it has full end-to-end SSL support, which is very useful. Like if you have an old legacy application that you still need to connect to a database, but the SSL handshake and overhead for doing that in a PHP application, for example, is too big, you could set up proxy SQL in the middle to accept the unencrypted connections locally and then connect safely and securely towards the database. And this is the use case we currently use it most for at PlanScale. If we have customers that don't have the SSL support currently available yet, we put proxy SQL in the middle to handle that for them. So we keep the proxy SQL on their side of the connection, so they can, over their local network or local socket even, connect to proxy SQL, and then proxy SQL handles the encryption that we require on the PlanScale side. So architecture diagrams for deploying proxy SQL. This is the simplest one. So you have your clients on one side, yeah, there, and then you have the proxy in the middle, and your client just connects to the proxy, and the proxy connects to MySQL. It's always recommended to have not one proxy, because that becomes your single point of failure. If your proxy dies, then the game is done. So in this case, there's 3, but you can scale that as many as you want. The proxies can talk to each other to share configuration. So if you configure one, the other ones will automatically follow. And then on the back end, you have the MySQL servers. You can see these are called, in proxy SQL world, these are called host groups. Like this one has one server, this has two, this has three. Important to know is that if you connect to proxy SQL, it will send your query to only one of the servers in the host group. So if it decides this needs to go to this host group, it only has one choice to send it to. But if it decides this is the host group it needs to go to, then there's two hosts in this one, but it will send it only to one. So it's not a good solution for write load balancing, because you will be writing to different servers, and that will lead to split brain. So that's not where you want to go. So if you have a host group, a primary, to talk to a primary, it should always be one server in that group. Another very common architecture, and this is mostly done in Kubernetes deployments, is you put your proxy SQL where the application is. Like you set it as a sidecar to your application, and then the client, the application, can talk locally over the local inside Kubernetes networking, or even to the local socket to connect, and then proxy SQL will handle the connection towards MySQL. And this is what we typically use when customers have issues with the SSL offloading and stuff like that. So we can put the proxy very close to the application and then connect to MySQL. This is a good architecture, but if you have a lot of pods, it's becoming very difficult to keep the proxies in sync. And so then you have the hybrid architecture that you can use. So proxy SQL the backend in the proxy SQL can be another proxy SQL server if you want, because they just speak the MySQL protocol. And so in this case, all the proxies here are configured with the same configuration, just the addresses of these three proxies in the middle. And if this changes on the backend, the only proxy SQL instances that need to be updated are the ones in the middle. And then these ones don't need to change. You don't have to sync them with anything. Only if one of those here would change, only then they need to know about it. But this is something that doesn't change that often. So, and also because proxy SQL on the client side knows whether a proxy would go down, like if you would need to do upgrades or whatever, you can take one of the proxies here down, and these ones will know, oh, this one is unavailable right now, so I won't send traffic to that one. And when it comes back, they say, oh, it's coming back, so I can start using it again for sending connections. So that's a good thing to have. Then we come to plan SCaLE, like where I work. Plan SCaLE is built on Vitess, and Vitess is originally developed at YouTube. So this is an application that was cloud native before cloud native existed. The first release of Vitess was done just weeks before the first Kubernetes release. And the guys at YouTube, which was also a Google company, they talked to the Kubernetes team, which were their colleagues, and they were like, so whatever we built here, this is actually ready for whatever you're building. And they were like, yeah, actually it is. It was a thing before Kubernetes came to be. We currently run a managed service in the cloud. We are currently offering publicly in GCP and AWS. There's no reason why we couldn't do Azure, but there's just not been a demand for it. So if anyone wants, we are fully scalable. We run everything on Kubernetes. Like all our databases are running as pods in Kubernetes. Vitess and VT.org, one of the components of Vitess, provide us with high availability. So if something happens to the primary, we can either let Kubernetes reschedule it to another node and continue working, but we also have like a tool, an orchestration tool called VT.org that will detect this and will promote a new primary from one of the replicas in the cluster. And on top of that, this is why it was developed initially at YouTube. It supports sharding. As you might know, YouTube has grown a little bit over the last decades, just a little. And so to keep scaling, they've quickly realized that they would reach the end of the capacity of the servers they could buy. So they needed to go to a distributed system where they could spread the data over multiple servers. And so Vitess natively supports sharding, and thus PlanScale also supports sharding. This is the Vitess architecture diagram. So all the way on the side here, you have your application servers, and they connect to something called a load balancer. Like, this is something you can roll your own, or you can use in PlanScale side. We have our custom load balancer that we offer. And so this is where you choose what you want. If you want to run Vitess on-premise, you can just put an ELB or TCP load balancer in Google in front of these things, and these things are called VT gates. And this is basically our proxy. And so your application connects to VT gate, and VT gate will accept MySQL connections and will tell you like, hey, you're talking to me as a MySQL server, and everything that's behind me, just to your application, just looks like one giant MySQL. But in fact, there might be hundreds of shards with hundreds of MySQLs, but to your application, Vitess will say, hey, here's a database, talk to it. We run in our Kubernetes clusters, next to our MySQL processes, we run a VT tablet. It's basically a sidecar process. Actually, if you think about it, MySQL is more like the sidecar process to VT tablet, because if you're talking about MySQL, it's easier to think that VT tablet is a sidecar. And there are multiple shards, like the tables can be sharded into different MySQL servers. And VT gate can know about that because this is all registered in a topology server. We use etcd for that. There are people that use Zookeeper with Vitess, but that's a minority. There's still a few people that use console as topology server, but we're looking to deprecate that in the future. And then you have things like VTCTLD, which is the control plane to control all of the things here. So if you would like to add a new tablet, you tell VTCTLD like add tablet, and then it will update the topology server and make sure that VTGate knows about it and all those things. VTOrg is what I told you about, is another block that should be here, but I couldn't find the image of it, so I left it there. And then on the back end here, you have MySQL, which is basically still the main storage. Our connection pool is not situated on VT gate level, but it's situated on the VT tablet level. VT tablet keeps connections to MySQL open, and the connections between VT gate and VT tablet, they're basically gRPC HTTP requests. That is very much easier to handle than keeping MySQL connections open. HTTP scales a little bit better. Then on PlanScale, we added our own edge infrastructure on the load balancer side. And our edge infrastructure is a little bit similar to what you would get when you use AWS edge locations. If you have an S3 bucket and you want to serve that from a local area, you can have an edge location that caches basically your connection. What we do is we terminate your MySQL request on the closest edge that we have. Like if you connect from LA, you will be terminated in a US West 2 region to make sure that you have the lowest possible latency, and then Edge will figure out where your cluster is and will connect you over the AWS or GCP backbone to your actual database. So to have the lowest possible latency, that's a good thing. And also Edge supports HTTPS endpoints, gRPC connections. So if you don't want to use the MySQL protocol to talk to MySQL, but you want to use like HTTP connections, you can. So that's supported by Edge. And that's actually also the initial use case for VT-Gate. Like initially at YouTube, VT-Gate, the applications talked gRPC to VT-Gate, and the MySQL protocol in VT-Gate is actually something that came later in the second phase, because we offer a MySQL service, so we should potentially also be offering the MySQL protocol. So that's then what it looks like in the global routing infrastructure. So you have the edge at the closest place you want, and then you have the databases. So the VT gates are the proxies, and then you have your databases on the back end. So wherever you come into, you can be routed to the right database and VT gates as you need to. And then we have a blog post where we took this glove to get it to 1 million connections. And we got there. So if you want to read about how we did that, there's a blog post there. But any questions?
I have a couple questions about the hybrid model for proxy SQL.
Yeah.
So I work on game servers, so latency is a big concern. So I'm running an external proxy, adding a hop to every request is kind of a non-starter. So first, doing the sidecar architecture, like what scale roughly does that start to fall over, where you would do those intermediary proxies, like tens, hundreds, thousands?
That depends on how you configure them. Like if you use the proxy SQL clustering mechanism, I wouldn't go over hundreds. But if you have a way that you can distribute the configuration for those proxies in a better way than letting them figure it out amongst themselves, you could go to thousands. Like if they don't have to rely on it on talking to each other, it's I know proxy SQL was originally developed at Dropbox, and they also have quite a lot of connections, so it's able to scale quite significantly there.
And then the other question is, the intermediary proxies, are those just there to keep the sidecar proxies synced, or do all database requests actually go through?
They go through there, yeah. So what you do, let me go to the slide. There we go. So basically, the reason you put these here is because this is more volatile on the MySQL side. Like if there's a failure on your MySQL end, you need to promote a new primary, or you need to recreate a new replica. And then proxy SQL needs to know about that. And if you have thousands of proxy SQLs to update, it's going to take a while.
Yeah, I guess theoretically, though, you could see a world where the intermediary proxies were just there to do the SCG job effectively, of keeping these sidecars so that you don't have 15,000 sidecars.
Yeah.
They don't all need to be talking MySQL. They can just talk to the...
Yeah, the easy part here is that it's just monitoring the health of the proxy here. So if one of these proxies goes down for the upgrade or for whatever reason, it just stops sending traffic there. So it's only doing a ping, like, are you alive or not? Whereas if you have to update the configuration, it has to be synced and it has to be stored. And other questions? Yeah. Yeah. Mhm.
Of course, in order to move all the caching and everything, actually you can do all that, so you don't even have to create the configuration for work, do all the SQL DB and stuff for a big amount of servers.
Yeah, right now we just use the MySQL client, the C library, and handle tooling ourselves, but it would be kind of nice to have like release some code just run off.
Oh yeah.
But yeah.
Take one bench.
Yeah, proxy SQL performance is really good for that. Like it really helps.
I guess one other question, sorry, just to get in the room. Is there a separate like client SDK to interact with proxy SQL? Or
No.
is it effectively just you point your same library towards it?
Yep. It's basically speaking the MySQL protocol.
You have to just create the user set and create the database mapping, and you actually,
Yep.
it's absolutely fast.
So it's like a drop-in replacement.
Exactly.
Yep.
Do whatever you want.
It basically does whatever you're doing now. It's also implementing the C library for MySQL client. Well, it's using, I think, the MariaDB library still internally. But yeah, same potato, potato. Anyone else? And we could all go to lunch.
a little bit. Say hello.
Hello, check. Sound check.
There you go.
All right.
That should be good.
All right, we can turn it off for now.
Great.
Hello? Okay. I guess we can slowly start, and probably some people will show up later on because it's lunchtime and there's expo hall is open, and maybe they'll join a little bit later. Today we're going to talk about design and modeling with MySQL, but design and modeling for databases, MySQL and Postgres. So, you know, it's put it this way because this is supposed to be MySQL track, but it applies for Postgres and other databases. We'll go through that, but before that, if you haven't connected, we can connect. My name is on the schedule also, or you could send me a request on LinkedIn. And my name is Alkin. I work in Sista Data. Some people call it Chista. And I'm the EVP of Global Services, where I actually handle the customer interactions and run a team of DBAs, focusing on ClickHouse on analytics. Previously, I was working in some of the services companies like Percona Pitian and PlanetScale, which we talked about in the previous call. And in my previous life also, I was an enterprise DBA. I worked on Informix, Oracle DB2, and SQL Server installations worldwide. So a couple of things that I've done in the past, so we'll skip that. And this is where I work. Why I put this over here, we're still hiring. So if you're interested on getting your workloads on MySQL or Postgres slimmed down and want to run some analytics, you can actually give it a try on ClickHouse. And ClickHouse, we'll talk about that a little bit later, but ClickHouse is a columnar-based database, which is outside of the context of this talk. So I won't get into that, but check out the SistaData.io or sistadata.com for the blog post and the information. There's also a DBAS that you can go ahead and sign up and try. All right, so as a captain and a sailor, I have to put in one maritime slide for every talk I make. So today's trivia question to the audience is, what is the name of this device or instrument? Does anyone know? Okay, good. All right, you got a beer from me. So it's called sextant. It has nothing to do with, you know, don't think that way. It's an instrument to calculate an angle between the two objects, and then it's literally used in 1800s for navigating in the seas, for getting the horizon, and the object could be a star or anything else. And then there's a little bit of a calculation behind it, latitude and longitude, and you can find where you are, basically. It's difficult. I have one, never used it. I don't plan to use it, maybe when I retire, but it's something is out there. So I bought it just to, you know, it's nice. But with the modern technologies, we use GPS and everything else possible to navigate, and for forecasting weather and everything. We have very complex and advanced systems to do that, but it's nice. So thank you for the answer. Also, we had a lot of discussions around the community. So MySQL community, as you can see, the room is not that full. Maybe there's a little bit of a split. I have taken some time to write a blog post about the community. How can one contribute to a community? And basically, I wrote it for MySQL because I come from the MySQL community, but you can contribute to any other open source database or other open source communities. And please take a look at it. The slides, we will share those, so you can basically get the link. All right, now that we have hopefully broken the ice, and we can look for the agenda. So today's subject is database design, and we'll cover some of the scaling and scalability options that we have. Some of the previous talks already covered for Yugabyte and for PlanetScale, for Vitesse, and I will also touch base those. And there'll be another talk after this covering the TiDB. And then we'll talk about integrating databases, and then emerging trends, which is going to be the distributed databases, where we can actually, if we have time, we can actually talk about, or open discussion over here. So I'll try to keep it light and not boring, because database design and modeling is sometimes you don't get to do a lot, because when you end up in a company as a DBA or a developer, there's already some sort of a database, and it's built by some tribal knowledge. Sometimes it's the business requirement comes in fast and quickly that it's actually taken as a scratchbook, and then it becomes a huge, large database, which is problematic at the end because you're there. As a DBA for the last 3 decades, I've ended up in many places with the same problem. Sometimes I did contribute to a design of a new schema or new database, but sometimes we had to deal with the existing design, which was a problem. So take a look at the history of the data model. So I come in somewhere in between over here, but basically the models that emerged on the in the 70s, they were like the network model, and then the network model was basically flat files and reading large files into like a database, a data store, one by one, sequential. Some might know that if you worked in like COBOL era, RM COBOL era, there was like a files in the, and it would just read, and maybe with simple index or not even a libraries. The libraries came maybe a little later, the ISM, CISM libraries, and then which became part of the MySQL originally. That's again about 30 years ago. So the relational model born in the heart of when the databases actually became more like a requirement for the businesses, and yeah. Okay. And what we're saying is relational databases became dominant in 80s, and the 90s we have faced the object-oriented programming, which actually came with the object databases, and in 2000s we started having graph databases, and now we are on the white column stores, NoSQL era of the emerging technologies in this era. So ClickHouse is one of those, the column store, which actually is opposite of the row-based system, which we will talk. If you look at this history, the emerging technology from the inception of the database or the data model to becoming commonly used technology, it takes about 10, sometimes 15 years. So yes, the relational databases became in the 80s, but businesses, most businesses actually started using Oracle Informix DB2 or UDB DB2, even SQL Server in the late 90s or mid 90s. So, okay. And because of the popularity of the relational model, currently it is still the most common used with a 60%, and there's also the other models that were used in the model. If you see hierarchical network and object-oriented model, they actually don't actually take as much space as the relational database models, but I think this list can be upside down in coming years. Maybe the introduction of the microservices and splitting up the data and the data models are slightly changed. Within those, there still relational model still exists. So if you look at the relational model, as we all know, for MySQL and Postgres, they're all organized in the tables, and it's row-based, and each row actually has their attributes, and then there are keys around it. We won't get into the keys on this talk too much. It's a separate talk. Keying, indexing, optimization of queries, all that is a separate subject. But this is, this is the foundation of the database design. So if you don't have a design that supports your queries and the business rules, then you'll have a problem with the whatever database it is. It's not going to be a MySQL only, but also on others. Okay. So one of the concepts that I would like to highlight is the normalization. So it's actually directly linked to the relational model, because if you have a relational model database that needs to be normalized, this used to be a thing in the early days, as we've seen in the history of where it was born. The data on the relational databases, on the modern, earlier versions of RDBMSs, they were not normalized. So this was a very big requirement to have data normalized and then become more efficient and basically consistent in itself. So, so what is a normalization? Normalization is actually basically reduction in redundancy, avoiding the redundancy in your table. So you don't have the same table repeated, same attributes repeated among other tables. And so this improves the integrity. You don't have to go and update multiple tables for it. And then also it helps the efficiency and the productivity of the database that you're actually querying. So, okay. So the other thing is, this is linked to the relational model, is the ACID properties. So we have to have atomicity and the consistency and the isolation, and also the data should be durable. So in order to basically do all of this in the relational model, you need to have all these properties applied along with the database operation. So going back to the database design, when you are thinking of designing a database with this relational model, you have to know these properties that the database will offer to you. And MySQL is ACID compliant database. So what we mentioned in the new era of databases, some of the emerging technologies like NoSQL or columnar databases don't necessarily comply with ACID properties. Hence, they cannot be used for transactional purposes. And also the infamous cap theorem. And so along the lines of ACID properties and the database design, you will actually have a problem to deal with is the consistency, availability, and the partition tolerance subjects. So we have to make sure that these are also aligned with the database design, which is the relational model in this case. Also, you're complying with these three. So I will get to where MySQL stands in here, but again, the cap theorem actually isolates the availability, partition tolerance, and consistency. Having these three, it's actually, I give this example to, think about you're in you went to a restaurant has amazing food, and the restaurant you go has a beautiful view. Maybe you're on a seaside or a lakeside, and the bill is very cheap. That is not possible. This is what it says. So if you compare to that, having all these three within the same database, you will have a problem with your database design and the model. So how does this happen in the NoSQL world, which is, again, outside of the context of getting into that, but knowing these are the properties of the theorem, you will actually have NoSQL having an optional workarounds for that, such as eventual consistency. So you will have a database, it will be consistent, but not immediately. So you can't do read overwrite, like you can't do certain things. So make sure that you are in that sense, because what we have seen in the last decade is specifically on MongoDB world, it actually had, or some of the other databases like Cassandra were used for relational model mapping, but it didn't actually work the way that it was supposed to. So this was proposed by Eric, and then there are trade-offs between the properties. So you will actually have to make sure that your trade-off is satisfied with the design. Okay. For the data models, we have a couple of key terms: entity relations, the attributes, and the relations between the entities. So these are the things that maybe the new generation of developers or DBAs don't actually pay too much attention. But if you have a proper design, these are the things that you will be actually having. So the other models are hierarchical model. For example, it's a top-down model, and you will have no relation between the bottom of the entities to the top. It will be only one way around. The network model was also popular in the earlier days, and it's no longer a thing. Object-oriented model is still a popular thing to be considered, and because the object relational model is still applied within the object-oriented programming and object-oriented ORMs that will actually apply these. And then there's the relational model, which is somewhat satisfies with the relational database management systems, database properties. And then there's also entity relationship model. So basically you would have a couple of examples. For example, customers order shipments. You can have a one-to-one, one-to-many, many-to-many relation, and visualize that. Make sure that your database is designed the way it's supposed to have, and nothing is redundant. So you'll have to actually apply the normalization, and then you will actually have a proper database design at the end. Unfortunately, we will not do a workshop over here. That would take a long time to do it. I would maybe later on sometime, that would be a good example of how to design a database from scratch would be an option, but I have a quick hint for that at the end of this talk. Okay, so let's go back to the entity relationship model. So you could actually have a somewhat entity relationship diagram in order to understand the database. Okay, so who actually has ever done an ERD, entity relationship? Okay, we have a few people. Again, I mentioned it's not as popular as it used to be. I used to work in large enterprise shops where nothing would go in production without having an ER diagram, and then normalization is applied, and then there's keys created, verified, checked, and then deployed in. So today we're not maybe diligent as much as used to be in the, like large corporations, but if you basically don't do all of these, you are going to be facing a problem at some point in your future growth as the database will evolve over time, which we will talk about a little bit on the scalability and how this gets into a problem of becoming one single database into multiples of thousands of maybe clusters of database globally. So how do we do this? We actually gather the requirements, which the business is supposed to tell you. Okay, we're going to actually have a new service, say a new payment system or new integration to some mailing system or something like that. We identify the entities. We make sure that attributes are identified. When this says attribute identification, what does actually ring you on? What is that actually meaning on that attribute? Basically, this is the data points. So I think this is another very important point, is the data type. So if you don't want to have a problem in the future, you would want to make sure that all the data types applied from the beginning properly. So there is a lot of experiences that we faced. Oh, this database is slow because they used a wrong data type for a wrong attribute, and it actually had a difficulty both indexing, making relations, and other problems. So after all of that, we build ER diagram, and then we construct that, and then we review and refine. As you build this, we actually apply the normalization techniques. And then basically, the ultimate goal is only having the reducing the data redundancy. Okay. In MySQL, interesting enough, there is a tool for that, and it's free, and no one uses it. So has anyone ever used MySQL? Okay, but you build databases, okay. There's some couple of people use it, but this tool has evolved and improved over the last decade a lot. It used to be very simple and didn't have all the bells and whistles. The last edition that I had downloaded and tested is actually pretty good, and it can do a couple of things. It can do the modeling, which is what it's supposed to do. But it does a reverse modeling also. Say you actually have a database, and you connect to a database, it pulls out and it gives you the visual relationship model, which is, I think, pretty cool, because your database can be small or big, but knowing visually the relations and how it's built, it would be very good to use this tool to do that. I did search for the Postgres version. There is none out of the box in Postgres, but there are a couple of third-party tools that you can actually pull this data. I'm not even talking about the paid versions. And then it does the query. It's a query editor. We don't necessarily use for queries or the administration in MySQL world. It's always like as much as CLI possible. But if you're a beginner and if you're kind of exploring it and there's a way of connecting to a database using Workbench, and then it can also do the validation, which actually can generate between the models and entities, it can actually check the validation for the design of it. The other thing that it does, maybe it doesn't mention over here, is actually it can also generate the SQL statement for it. Like you can design a database over here and then tell it to generate the SQL syntax for it. You can take it, copy and paste it somewhere else, and then execute it. So it's actually pretty good. So you don't have to type it by hand. It's a useful tool. So we mentioned about the ER diagram, and then we built a database, and then we think that it does satisfy the need of the business, but then we also still need to check about the normalization. So the first normal form, we actually have a primary key for each table, and then it actually represents that each row and only atomic values are in it. And then there's the second normal form. So it goes on and on like this up to fifth normal form, but normally you are around second normal form or the third normal form of a table design with the entity relationship. And then this is something, it's not mentioned in any of these slides, but there is also denormalization. When it comes to be too broken down in the system, again, you have a problem. I had been involved in a couple of denormalization efforts because the table didn't have the properties of the attributes of the data that it needed, so it had to gather from somewhere else, which actually also an overhead for a database operation. So you also want to minimize the joins and maybe even like a bad queries, Cartesian products that might be caused by reading two tables, joining the rows, then maybe it's too much to have beyond third normal form of the table. So this goes to, this technique is not intended for a single table. It is intended for the main relation of the data points. So basically you get to the primary keys, and then you make sure that you're separated the data to different tables, but not redundant. And then build the relationship, and then you actually apply these techniques, and then you remove the partial dependencies that is not suitable. So no non-key attribute depends on just part of a key. So if the column in our case is not a key, should not be part of the primary key of the table. Okay, so we mentioned originally for the asset properties, and then there is part of the asset properties. You also have isolation levels, which again link to the data integrity of our design. So we're designing a database, and then we made sure that it is asset properties are provided. We paid attention to CAP theorem. We did some normalization, but we still have to make sure that our access of the database is basically isolated. Why this is needed? Because we have concurrent access to the same data set, and if it's changing by different users, different connections, it has to be isolated from the other transactions. And there are different levels of isolation. And in MySQL, again, we actually have a repeatable read as a default, which actually works pretty good. I don't want to get into that too much in internals of it, because it's not part of this talk, but we actually balance the consistency and the concurrency with the isolation levels. And MySQL does a pretty good job doing that until things get distributed. So, which was part of the earlier discussions, maybe in the next talk also. So we have to choose isolation level carefully, and at least be aware of there are isolation levels that can be set by a client, which may be not in your control. So, all right. Scaling databases. So with that said, database, we created a model, and then we designed a database considering all the factors that we've gone through in the last 20-something minutes. When it comes to scaling, some of those properties will become a challenge. So why do we need to scale database? Maybe there's an exponential growth, the business actually booming, and so you need to set strategies for the scaling. Whether you would isolate a database per requirement, it could be per region, per country, per city, or you would do some other techniques to do that. Basically, this is what you will have to consider for both performance, reliability, and the availability. So having a database scaled, not available, things falling apart, having a latency, we have seen that a lot, and that's part of the deal. So there are some techniques that I will just highlight and overview those. For example, sharding, there's replication. Replication for MySQL is native, out of the box. Matthias in the previous call gave a highlight of those, but if just for those new people, if you weren't in this room before, it does an asynchronous replication out of the box. You don't need to buy or set up something outside of the MySQL itself. Caching, and then there's other options in the cloud also that you can scale the databases within the given context of the model. Oops. So we identify two ways of scaling. One is the horizontal scaling, the other one is the vertical scaling. So vertical scaling is a little bit more known method of doing it, for just adding a new node or a larger node or a bigger node and then getting that. Horizontal scaling can be a little bit complicated. You may need some other tools, some other coordinator, some other router or proxy or something like that. So be aware of that. How when you get there, you need to scale the database. You can't just keep putting in the largest instance of your cloud provider or your home machine. So basically, what we're doing over here is expanding the capacity of the database that we designed. Okay. So in the vertical scaling, we can actually have a couple of options over here. We actually have adding a new node and increasing the CPU. We mentioned that, and what we take the vertical scaling is a short-term solution until we actually have a bigger term or a roadmap in our hand to have a solution for scaling the database. So don't take the vertical scaling as a solution itself. It's just usually short-lived initiative that doesn't actually scale itself. So in the previous call also, previous talk also, Matthias mentioned a proxy solution can be a way of scaling the database because out of the box we have replication, but then splitting that replication into, for example, read-write, you can scale the reads with using replicas, and then you can use the MySQL replication application hitting that server. There's more complex drawings on his slides, but I didn't go into that much of a detail because these are operational problems, a part of the scaling, which I link it to our design and model. So you have a design model that doesn't actually comply with this solution, that's not going to work again. So in order to have that, I mean, I've seen databases just like one big, terabyte memory, single node database that you can't put on proxy or anything like that. There's nothing you can do about it. So proxy solutions are not limited to proxy SQL. There's a MySQL router, open source, and then there's people that's been using even before these existed, like HA proxy or other TCP proxies out there. MySQL has a different solution. There are many clustering solutions around MySQL, but one of the MySQL's native solution is the InnoDB cluster, which consists of a group replication and MySQL router, and also a supporting tooling around MySQL shell. So then you actually have a cluster itself. You can do primary and then secondaries underneath, and also you can have a cluster set around it. This is another way of scaling this. This could be like US East, US West, and Mid, and then you could actually scale these, connect all of them, and now you have a InnoDB cluster set around it. This is all of these, like this looks a pretty complex drawing, but all of these are natively supported in the MySQL ecosystem, which is amazing because, group replication is alone a cluster set. It uses some consensus algorithms. I don't know, again, it's not part of this talk, but there are some known consensus algorithms that to make sure that these actually work and talk to each other and also comply with the asset properties of the database within the relational model. Vitess, we talked about Vitess on the previous call also. Vitess is made for MySQL sharding framework, and it has the similar modules, like it's got the VT gate as like a proxy, and then there's a load balancer before you connect the databases and you can shard. This is basically intended for horizontal sharding. So 1 to n, meaning each shard is itself a cluster. There are 3 nodes in it. It has 1 primary and 2 secondary. And if something happens to this secondary, it just fails over automatically, and then it still have that. If you're running on this one with an operator in Kubernetes and all that good stuff, the new emerging technologies, you would actually have immediately initialize new host and then add it to the cluster. So the sharding framework allows to go pretty much unlimited in this case as the limit of your hardware or cloud resources or credits. So for more, we can check the Vitess.io. I have links at the end. Before going over to the serverless, there is a TiDB, which we will have a talk on. The next talk is that. There's much more comprehensive information about TiDB provided with the MySQL protocol. TiDB also solves many of the challenges of scalability on the relational model. So I have a link at the end, but no slide for that. There are also serverless options. So apart from the manual implementations or the frameworks or the open source tooling, some orchestration done around the database model, you can actually have a serverless MySQL solutions. Within the serverless MySQL solutions, most popular is AWS Aurora. Google Cloud has some solutions around it. Pretty much every cloud provider offers MySQL, but not necessarily scalability options. Aurora stands out over there. There's also PlanetScale, which actually uses this technology behind the scenes. And you could actually have a database that can scale unlimited if that was the requirement of the business. And you could still use the relational model with all the other properties, including ACID properties and the isolation. So these serverless, what do they actually provide at the end is actually serverless MySQL or Postgres or other database implementations. Actually takes off the burden of operational tasks, and they are all managed, automated by the systems that they've been hosted. So they're managed services, managed operations, operational databases within the cloud. Okay, so the future of databases. I think earlier today, maybe you were here, there was a talk on the Kubernetes talk. So we have a sub Kubernetes ecosystem called data on Kubernetes. So having stateful workloads in Kubernetes is something that's emerging technology. So you actually integrate with those technologies again, and then you can actually run different workloads underneath them. And one of them is running an operator. Operator actually runs the database operations for you in the Kubernetes, and then you can actually have a very scalable and I think emerging and more modern technology, which can be integrated and adopted to other technologies. So for example, I am running a workload that is designed and running on Kubernetes, stateless workloads like Nginx or any other implementation. Where do we put the database? I mean, database needs to sit somewhere in there, right? Like you can't actually have like a standalone database outside of your operational Kubernetes cluster. So you would actually have to adapt to these new technologies. Maybe it wasn't a good idea 5-10 years ago, but it may be a good idea now. So so you need to actually leverage the new technologies and new ways of doing that, which will allow, again, AI, machine learning, and all that new buzz. Okay, why did we talk about this today? This was the idea that came to me as from this book. This book, I've been working on this book for the last 8 months with my co-author. And this was actually good to go back and look at how the database fundamentals used to be and focus on that. This is on pre-order right now. It will be released this summer. And so hopefully you'll get a chance to read this book and with much more details than today's talk itself. And this was my previous book. We spent a lot of time on about 2 years on this book together with my co-author, Sveta. And this also actually has pretty good information if you are new to MySQL or you have some challenges with MySQL. Among the other set of very good books on O'Reilly, you can actually have a take a look at this. So I put this one on here so that people can have an access on the slide deck. And this is it. Thank you very much. Are there any questions? Thank you. Oh, I think we have a couple of minutes for any questions. All right. Well, thank you very much again. Thanks for listening. Oh, we have a question. Yeah. Partition tolerance. So partition tolerance is, Sunny, do you want to answer that question? He's very good at partition tolerance. So you are actually partitioned your connected nodes, but system still operational even that connection is broken. So the algorithms like Raft, Paxos, and some other algorithms that are similar to that, these are like basically computer science algorithms that creates a consensus among the nodes. If you have the majority of those, then you can continue. And if you lose the majority, it halts. Some systems actually say, okay, I'm not going to do anything because now we have a double-headed dragon over here, which may cause more problems than it is if the application writes into two nodes at the same time. So, split brain. We had that in our lifetime also. All right, any other questions? Thanks, Sunny, by the way. All right, thanks a lot.
works. Maybe something needs to switch on. Oh, shit. Oh, shit. Okay, we can sort of start, I suppose. Yeah, 8 minutes. Yeah, so we're going to talk. Wait, this is too loud, or is it only me? Is it okay? It's okay? Oh, fine. So yeah, we'll talk about beyond MySQL and what's been happening in this space for the last 8 or 9 years, because TiDB or PingCap has been around for 8 years now, and it's maturing into a fine product. And it's a distributed SQL, unlike MySQL, which is like a single node, but then you have add-ons like replication and group replication that I'll talk about, and then I'll talk about what TiDB is and how it works. So if you have any questions, feel free to ask me. You can ask me later, but even during the talk, we can interrupt. There's not that many people, so we can figure it out. So a little bit about myself. I work for PingCap now, and I've been at PingCap for 2 years. I've been working on databases for a long time. I used to be the lead at MySQL of the InnoDB team, and that's my Twitter handle. We have this raffle thing going on, so if you have you want to join the raffle, you can just scan the code and That should work. Okay, everyone's done with it? No. Okay, so a little bit of history. It's pretty long. So this is more about MySQL replication or history. So it started as a single node system. In 2000, they had replication, which was just moving SQL statements from one MySQL to another using the bin log. It's asynchronous, and it's been asynchronous since then. Group replication was released in 5.7. It supports multiple writers, but that has its own issues, and they don't recommend it, but they have it, so I should mention it. Default is still asynchronous. It has consistency. It's eventually consistent, so it's not synchronous. Replication lag is an issue. DDL is a big issue. If you have large tables, and it's a DDL itself is a single node operation. And you can get stale reads, which is because it's asynchronous. And the maximum number of nodes in a single group is 9, which I don't think anybody runs. They usually run 4 or 5. At 7, the performance is pretty bad. The next evolution in the MySQL space was with MySQL Aurora. It was announced in 2014. The big innovation there was that the SCaLE and storage, the compute and storage were disaggregated, so you can run them independently. So they had a storage layer, which was scaled, and then they had one single writer, and they had multiple readers, and they replicated the redo log of InnoDB. It's still limited to 128 terabytes, and this is because of they use a single table space to store everything, and InnoDB is actually limited to 64, but with a bit of trickery around bit fiddling, they've moved it to 128 terabytes, but it's still a single table space that is shared, part of the shared storage. So I won't go into details of Aurora. This is just a simple list. There is also Vitess. It's more of a sophisticated proxy over a cluster of MySQL nodes. It requires manual sharding. The application needs to be aware of the manual sharding, so your application changes. The sharding ID has to be passed around. Resharding is, as I've said many times, it's like a masochist's dream. It's just painful at scale when you have to do it. The latency can be lower with this architecture, though. So if you are hitting one single node for your requests, the latency will be much better with the Vitess architecture than the others, but you have to pay the price of how it all works. It doesn't have consistency across all the nodes. It doesn't even support repeatable read beyond a single node. So when you do 2 nodes, if, let's say, as an example, if you have your commit is over 3 nodes from the application side, and 2 of them commit and the third fails, there's nothing Vitess can do. That burden is moved to the application developer to figure out what to do. So it can cause bigger problems if you don't understand how it works. So that has its own problems. The next big breakthrough was in Spanner. So they used the same idea from MySQL Aurora, the disaggregated compute and storage, but they have proper distributed transactions, and you can have multiple readers and writers. And the storage itself can be scaled out almost infinitely, but obviously there are limits, but it really was. TiDB, was inspired by Google Spanner. So the TiDB founders they were working for an internet company in China. And one of the big problems, and these were the good times, when things were scaling really well in the mid, like 2010, 2012, and they were constantly sharding and resharding to handle that scale. And they were using MySQL. And they thought there must be a better way to do this. And so when they came across Google Spanner paper, this inspired them to try something in the MySQL space on how to scale like Spanner. And the current architecture is version 2. Version 1 was writing the SQL code or node and then having HBase, and that didn't scale well, and then they changed the architecture to what it is today. So what's TiDB's unique value? It's open source, it's reliable, it works at hundreds of companies, if not thousands now, especially in China, but also here, Databricks, Pinterest, a few others that we can't use, but it's working here in the US too. It's multi-tenant ready, so for example, at Airbnb, I think, they consolidated something like 440 Aurora nodes, MySQL Aurora nodes into 50 or 60 TiDB nodes, and they consolidated their applications to run on that cluster. It's versatile, it can run across games, logistics companies, web scale companies, any kind of load you can throw at it, it does pretty well. It's MySQL 8 compatible, and it's really trivial to set up and start. So if today you want to try it, just go to tiup.io, just download, do a copy and paste, and it'll be up and running in 5 minutes. So it's very easy to set up. It's that same tool that is used to scale it out to thousands, if not hundreds of nodes. And you can start with the sandbox immediately if you want. So it's really easy to set up. So these are all the companies that are using it in production. And there are many of these that are running it at 800, 900 terabytes. And at that scale, there are many things that MySQL is not so good at. DDL is, for example, like a big problem. And I'll get into the details of how TiDB works and handles all that stuff. So first we'll do the design fundamentals, then a bit of resource control, how you can use resource control for multi-tenancy and other things, how online DDL works, and some of the tools that are part of the whole TiDB ecosystem. So this is our reference architecture. And there is one part of this that I just want to highlight, and that's what's called TiFlash. TiFlash is what gives TiDB the ability to use the same data for analytic workloads. So in the same query, for example, the TiDB optimizer can send part of the SQL requests to the OLTP nodes, which is TiKV, and anything that can leverage the column store with its own MPP engine, that goes to TiFlash. So this is like called HTAP. So it has three main components. If we take out TiFlash. TiFlash is optional. You don't have to use it, TiFlash. It's something called the placement driver, which is like a metadata server. TiKV, which is the scale-out storage system, which also does transactions. And then there is the SQL layer. And these are the three main components. And you can do OLTP. It uses Raft or consensus. Data consistency is guaranteed by TiKV. TiKV is an Apache, is a CNCF graduated project. So it's region, so people who are familiar with, let's say, Google Spanner, region is the equivalent of a tablet in Spanner. Or you can think of it as, if you don't know what a tablet is, think of it as a page. That's the closest you can, if you're used to database, it's like a page. It's fault tolerant and it works across availability zones. So one other thing you can notice is that you have 4 nodes, and let's say you look at the little arrow there. So think that region or page or tablet is spread out across 3 nodes, 1, 3, and 4, and then it's also replicated to the column store and converted into the column store format. So what that means is that each of these pages, there'll be 3 of each, is a raft group. So each page is part of a raft group. So what is replicated is the page, not the entire node like you would have in, let's say, MySQL like group replication. So each page is a replicate. This is how it achieves scale out. This is the core difference. So if you have 1 million pages, all pages are then distributed across. So if you have like 1,000 nodes, by default it uses 3 nodes for redundancy. You will have all your nodes spread out, and how they are spread out is something that I'll talk about, and that's what PD does. So I'll talk about that in a little more detail. So a region is really it's logical scale unit. So think of it as a page if you can't relate it to anything else. So everything that's got to do with moving data around is around the concept of a region. So as I mentioned, a replicated region is a raft group, and a single node can contain many regions. But each region will have only one leader in a raft group. The other two are followers. And all the data is stored on RocksDB, and there is one RocksDB per TiKV node instance. And all the rows in a region are ordered. There's a whole story behind this, because instead of selecting hashing, we selected this is because we want it to be an OLTP database where range reads are important, and so order gives you that advantage. So it doesn't do any hash partitioning, it does range partitioning. So the rows are ordered. So it's important for OLTP queries. So what's a placement driver? It's a metadata server that coordinates the entire cluster. It's a stateless piece of machinery, and it uses etcd for its own HA. So you can think of it as that you don't want a single point of failure. So each component of TiDB is also, there are multiple of them. And because this is the metadata server, you want this data to be HA and you want it to be resilient. So it runs its own etcd to maintain its own state in its own cluster. But the process itself is stateless. So I can just start one up, point it to its own cluster, and the cluster, it stores its data inside TiKV. So remember that. Some of it, not all of it, but some of it. So it's the brains behind the whole TiDB cluster. It's what controls everything. It decides which page goes where, if there's a failure, what to do, which nodes need to be copied. It monitors the CPU, the disk, and everything else across the whole cluster, and load balances dynamically. So these are very powerful things that you cannot do with existing MySQL solutions. You just can't. So this is really genuinely the next level of what a database should be, a distributed database should be. And this idea is all from Spanner. It's not as if TiDB invented any of this. So it handles, like I said, it handles dynamic distribution handles node failures. It also handles cluster config, so it can do add nodes, remove nodes. If a node joins, leaves, it monitors, it knows what to do just in case node capacity increases because the node has gone, you've started something else up, and the old node comes back on. So it manages all those kind of use cases. You can do multi-zone deployment and for disaster recovery and stuff. So these are the things that I was mentioning earlier. So at the node level, it connects the total and the free disk capacity, the number of regions there are on that node, the data writing speed of that node, because all this is taken into consideration when it decides to move data around dynamically. It looks at the snapshot, so because it uses LSM, it can just take a snapshot and transfer it in case it needs to build something. It looks at it monitors the CPU, tagging I won't get into. It looks at, so the next one is actually very interesting. So it also, for failure detection, it monitors heartbeat messages from all the cluster. So it knows where the leaders are, it knows who's disconnected, it knows which node, what's being read, what's not being read. So what role does it play beyond this? So now imagine I've run an SQL query from I write an SQL query to the SQL node. The SQL node is stateless. It doesn't know what to do. So the first thing it does is, after it the optimizer has gone through the query, it will then ask the PD for the location of the data inside the cluster. So once it gets the address of where all the data is, then it goes to, so let's say the data is spread across, let's say you have 3 node cluster, the data is spread across, there's a primary on each of the 3 nodes. It will do a parallel fetch from all 3. So it does true distributed access of the data. and it gets the address from where to read the data from the placement driver. As from the name you can tell, it tells you where the placement is of the data. So what are the scheduling strategies it uses? So there is, basically you want to know how many, you want to specify how many nodes you want in your storage cluster. Then you want to know how do you want the placement to be per node, per rack, per node, per zone. You can specify all these rules, and the next few slides, I'll show you the syntax for doing so. You don't need to do all these, but there are specialized cases where people want to do this sort of stuff. They want very fine-grained control over where to place their data, and this could be for all kinds of reasons. It also balances the space utilization across the cluster. Just in case you want to move data from one cluster to another because you want to take something down for maintenance, it can do all that stuff too. It does hotspot detection and mitigation, so it'll start splitting up accordingly, right, dynamically. These are really, in my eyes, very powerful features. It's also, it has a governor which decides how much it should interfere and start doing scheduling, and you can control it. By default, it's sort of set very conservative. It doesn't move things around too much. But you can control the rate at which that also works. So you create a placement policy using standard SQL. There's no flags or anything. You don't need to start up or do anything. And I won't go over the SQL. It's fairly straightforward. You create a placement policy, and then you can attach it to a table. And you can use DDL for attaching that policy to an existing table too. So it gives you the flexibility to do a lot of things. And you can drop it, and then it goes away, obviously. So now we'll move on to the other component of the TiDB cluster. And that is the TiKV distributed storage engine. So this is what gives TiDB its scale out property. And the other thing that this TiKV does is it implements a distributed transaction protocol called Percolator that also came from Google. It's not what Spanner uses, this is what TiDB uses. It uses a modified version of Percolator to implement this. So all the TiKV nodes implement this distribution protocol. Because the SQL nodes are now stateless, when they talk to TiDB, the transaction part is handled by TiKV. So it simplifies the general architecture. So you can sort of visualize it as a distributed and ordered hash map that is designed for high performance and reliability. So just assume that all your data is just one large file that's divided into regions, and it's being shuffled around constantly by PD. So you can visualize it like that. It's a fairly simple idea, like conceptually. So let's take an example. So let's say you have, can you see it? Can you view the table? So let's say you have a table. It splits it up to 3 regions. And so if you have 4 nodes, it sort of places them evenly across the 4 nodes. And you can see that TiKV1 is slightly less loaded. So if the new page is created, it'll probably put the leader there and move the other followers onto the other, maybe TiKV3 or TiKV4, depending on the characteristics of the node. So maybe TiKV1 is a more beefy node, so it'll move more pages there. So it monitors all this because it knows the statistics and the performance characteristics of each node. So it's quite clever. Oh, sure.
So all those 4 nodes are the same data center?
They can be anywhere you want. It doesn't matter. They can be across continents if you want. But then you have to pay the latency price of, let's say TiKV4 is in India, for example, right? And the leader is TiKV1, and that's in the US. So the consensus protocol now will have to send messages across geographical regions to guarantee consistency for, let's say, any region that's where the leader is inside TiKV1. So they can be placed anywhere, but then like anything, you can't defy the laws of physics. You have to pay the latency price. So the way that people deploy these things is slightly different in practice. They will never do the kind of deployment I just described. Nobody will do that. They will partition the data first based on their applications for local access, and then have as little cross-region, cross-continent traffic as possible. Just like any other database. I mean, you have to pay the price for anything if you're doing any cross-continent. But there's nothing stopping it conceptually from doing so, is my point. Yeah? So, one problem you have with distributed storage is that, now imagine your SQL node has to work like a traditional SQL optimizer. So, if it needs data from, let's say, 3-4 nodes, let's say you're doing an aggregation. So, the last thing you want to do is fetch all the rows into your SQL node over the network, and then do your aggregation inside the SQL node. A massive amount of traffic will be extremely slow. So what you do is you do the standard query pushdown. So each TiKV node also has 4 types of query pushdown handlers. Not 4, 1, 2, 3, 4, 5 of them, right? So there's so let's take the last one as let's take aggregator as an example, right? So my query has like some select count star across some table. So what it'll do is it'll look for the leaders across the cluster, get them to do the calculation of the data that they have, and send the result back to the SQL node, and it'll do a very simple aggregation of the results that it gets. So it doesn't have to fetch all the rows to do it. So this is called the TiKV coprocessor. So each TiKV node works on the data close to the data. It doesn't, so the whole idea is to minimize moving data around to do results. In reality, if you want to do a count star, you're better off using something like TiFlash, which is like even faster. Because it's a column store, it'll just, let's say you're doing a sum over a column, it'll be faster than any row store. But anyway, that's what the coprocessor does. And it's inside every TiKV node, is to reduce traffic and make things faster. Let's say you want the top, you have a limit 1 on your query. That will also be done inside every node, and then the results will go there, and then the optimizer will give you 1 row back. It can, yes. Even for one query, it can spread it, it can. So if you don't have TiFlash, then everything goes to TiKV. But if you have a TiFlash, because you want super fast analytic queries, the optimizer can figure out what it needs to do to fetch the data from both the column store and the row store in 1 query. So there's no MySQL code in any of this. This is just all written from scratch. So it's not, it doesn't have any of those legacy single-threaded, single-node, monolith problems. This is like a true distributed SQL. So I won't go over too much of detail about how Raft works, but just as a rough idea. So the core idea of Raft is to elect a leader, and the writes go through the leader. So whenever the SQL nodes need to do any writes, if you have, let's say, 3-node Raft group, it will only write to the leader, because the leader is always known to be the latest data. The follower may not have the latest data. It may be in the process of sending data or whatever it is. And the data is not considered durable until a majority of the nodes in the cluster acknowledge the write. So the leader is always the source of truth. And that's where the SQL nodes get the data from and write the write to Raft, and Raft then spreads it around, but the reads come from the leader node. So this is like a diagram on how it sort of handles failure. So let's say you have 4 nodes, and you can see there's heartbeats going into the placement driver, the cluster of placement drivers, and suddenly a heartbeat for some reason gets interrupted. That means there's a timeout, so it says if it's timed out. It's all configurable, and then it'd say, okay, then that node is down. Let's assume it's genuinely down. Then it will start initiating an election between TiKV2, TiKV3, the blue region, and then move the data to TiKV1 to resolve the problem automatically. So that's what will happen if it detects a failure of TiKV4. So you don't have to do anything. This is all happening automatically behind the scenes. So it's self-healing is like the more marketing term around this. So TiDB supports read committed and snapshot isolation. So the snapshot isolation is mapped to MySQL InnoDB's repeatable read. There are some minor caveats which are mentioned on the website, but they're too minor to talk about here. It should, for 99.99999 of the applications, it will just be repeatable read. So it uses, I mentioned this earlier, it uses an optimized version of Percolator for distributed transactions. I won't go into too much of detail. And that requires a global timestamp. That timestamp comes from PD. And they're also used for MVCC, which is a fairly standard MVCC. One thing that I haven't mentioned is perhaps how data is represented. It's not important, but I'll mention it. So the data is mapped into a key value store. So let's say, as a rough idea. So let's say I have a table T1 and it has an index I1. It'll be written as, the key will be roughly speaking, like T1 underscore I1, so that you can locate the data like that. So that's mapped like that. Also, it can optimize for short queries. So if you're doing single write, let's say auto commit single insert, just let's say because you're going to just one region or one page, it can optimize that to a single phase commit. But anything that touches two regions can only be solved by two-phase commit. So you have to send it out, and then they have to say, yeah, we both have understood, and then it has an optimization to reduce one part of the Percolator protocol, which I won't go into. So it's optimized Percolator. But for single node updates, it can do it in one-phase commit. Because that's easy, that's trivial to do. So it's very fast for short transactions too. But if they are across pages, then two-phase commit kicks in. So this is like a classic optimizer, and this is how TiDB does it. The only difference between MySQL and TiDB is that it also has a distributed core processor, and this is the one that question you asked. So this can talk to TiKV and TiFlash at the same time. So it's aware of the topology, it knows what to do, so that's what that does. But this is a fairly straightforward optimizer architecture. I don't think there's anything special except for the distributed core processor. So it's aware of the layout of the data. So this is an example of the question that you asked. This is how it would work in practice. So the executor would figure out which is will the fragment of the SQL query benefit from fetching data from the MPP engine in TiFlash, or will it be easier to get? So whichever parts it needs as part of the query plan, it'll get those parts and then join, combine, or whatever it has to do. It'll do it inside the executor. So that's how it'll actually work. And these, again, so this is a real example of how in a single statement, the table scan will go to the column store, but the other parts it'll go to TiKV where it needs lookup. But for the scan, it'll go to TiFlash. So that's, if you look at that query, that's roughly how it will solve that query by going to TiFlash and TiKV at the same time. So it's optimized to give you the best, most optimal result if it's the data is on column store and on row store. Okay, resource control. I'm maybe running out of time, I think. Anyway. So you can, I'll just skip to this part where it's the actual action. So what the thing you want to do with resource control is, there is one classical problem which every database has, and that is you have short queries and then you have long queries. And you don't want the short queries to suffer because of long queries, because users care about the latency of the short queries. They don't care so much about the latency on what they know are queries that are going to take some time. So how do you, this is like a classic universal database problem. So that's one problem. The second is you want to manage multi-tenancy. So you want, this is some application that's touches this part of the database, and I don't really care so much about this, and it can run a bit slowly, but these queries that run on this other schema or database, they should not be impacted, and they should be much faster. So there's a concept that TiDB has called resource control. So this allows you to have multi-tenancy and consolidate your instances and reduce your cost. That's how people are using it, and that's where the request came from. So you want to check your CPU, you want to check your I/O. It currently doesn't check network, but it does check CPU and I/O. And it works a little differently in TiFlash, which I won't go into. I'll just talk about the TiKV part. Also, backups, you don't want to run them at top speed. You want backups and any compaction or anything you wanted to run in the background and not chew up all your CPU and your I/O. So all of these are scheduled through the resource group. So it's a logical container, and there are three important parts to this. One is, let's say the bucket size, more easy to say this. And this is how much quota you give it per second, so that's the backfill. And you specified when you create the resource group. The second is a priority, low, medium, high. So these are, which means when the query is broken down inside TiKV and when the information is sent from the TiDB node, the scheduler will look at the priority and decide whether to give it more CPU time or disk or not. That's basically it. Burstable is interesting. So if your resource group has burstable, you set it to burstable, it means that if there is excess capacity, but this query has run out of its RUs, don't worry about it. Give it any unused RUs, that this is that important. And the other thing it means is that this query is so important that even if the system is loaded, this must execute. That's the second property it has. Don't suspend it because you want to balance the system out. Make sure that if there's unused resources, give it to any query that's running in this resource group, and it must run all the time because it's that important. So that's the burstable flag. So the whole theory behind this actually is from a VMware paper from 2017 or 18, I can't remember. And so it uses a weight and constraint based scheduler. I won't read out that whole text, but the gist of it is, one is proportional sharing, and the other is like a minimum time that's required to run a query. And there are different costs. Like a write is the equivalent of 8 storage reads or 2 read batches, because writes are considered more CPU and disk intensive, let's say. And 3 milliseconds that your query runs is considered as 1 resource unit. That's how the calculation is done to balance and schedule everything. So it's fairly straightforward. How do you set it? You do it through SQL again, no special syntax. So you go create resource, it creates a resource. You can even say calibrate using the load from this time to that time, or from this time and duration 20 minutes, and it'll look at the historical data and calculate and calibrate and figure out what the resource unit quota should be for whatever you're looking at. So you can look at historical data and calculate these things too. So it makes it really easy to set up and use. Then you can fine tune it by hand if you want. I mean, this is required for any multi-tenant system, and this is why in my talk I wanted this to be like the next generation where MySQL should be going. So how do you do these things? So you can create a resource group. In the first example, it has burstable set, and RU per second is 1,000, that query can only consume 1,000 RUs. You can use regular alter resource, set the priority high, change the RU per second, you can drop it. You can say show or select from information schema. So you can do all this using just like a regular SQL. It's very powerful stuff. Here's the other interesting part. You can do it at the user level, session level, and the statement level. So the granularity goes right down to the statement level. At the statement level, you give it the regular SQL hints through comments. And otherwise, it just works through specifying whichever user you want to set it to. So you can tag queries and say, this one I want to run as per the configuration of that resource group or some other resource group because, I don't know, that's just what you want to do. So this is just, I'll hand wave my way through this. So this is how it works. There's the TiDB SQL server, the storage nodes, which do the scheduling, and the data of the source group is maintained by the metadata server, which is PD. And so there's the admission layer, then there is the calculation part of it, and then the scheduling is done inside TiDB, because that's where you are accessing data, that's where you're spending your time in doing the real work. So the TiDB's calculation or optimizer is not counted in CPU usage, it's only in the actual processing of the SQL statement. So if there's any question, you can ask me, but it's fairly straightforward-ish. Oh. Okay, this is another very interesting thing that TiDB has. So in a distributed database, you have lots of storage nodes and lots of compute nodes. And you want to leverage this for your work. You want to spread the work around. You don't want to be working on one node and all the other nodes are just idle. You want some jobs to be working across your entire infrastructure. So the distributed execution framework does exactly that. Currently, we use it for background tasks, but we plan to make this available even to foreground tasks. So you can spread the work around across low load. Let's say I have 10 compute nodes and I have 20 storage nodes, and I want 5 of the storage nodes to do DDL, and I want 2 of those other nodes to do something else, then the distributed execution framework will take that task and spread it around. And currently it works for DDL, import, TTL, analyze, and backup and restore. So you can control what each component in your cluster actually does. So the detail is like a talk on its own, so I'll just skip that part. Yeah? Sorry?
Let's say that I'm importing a big table.
Yeah?
I specify.
No, the data will be spread out as per either your placement rules or the default placement rules. But the way you import data is actually much faster to do it. Because I'm running out of time, I'll probably show you, because I wanted to run this. No, I'll show you. This is because just in case I'm running out of time. So you can generate the SSD files independently and import them directly, rather than insert them row by row. So if you're running large installations, you don't want to be inserting rows through SQL. You just build your SSD file through a tool that we have, which will build it offline, and you just instantly attach it to TiDB, and it'll spread it across the cluster. So that would be if you have large data. If you have like, I don't know, a 500 or 100 gigabyte file, you can probably shove it in. But if you have like a 1 terabyte file or 2 terabyte, this is what you want to do. This is built for very large type of data, but it works even with small data. I mean, it's not that you can have a 3-node cluster running on your laptop and it'll work. But if you want to scale, then you want to do 1 terabyte, you build the SSD file and just shove it in separately. So online DDL, so this is a very big thing for anybody who's dealt with DDL in production and large data. In MySQL, one of the problems is you have to acquire the metadata lock when you do when you externalize the change of your schema. So what that does is, you have to wait for old transactions to finish, and it's a single node operation, and all new transactions are blocked until that change is done. All transactions are blocked. And on a very busy system, this is a problem. Where it's not busy, it's not a problem, because then it's like instant. But on a very busy system, and where transactions are slightly longer than, you have to wait for that thing to finish. In the meantime, updates are coming in, the InnoDB DDL log is being filled up, and that has to be applied, and all sorts of things are happening. And this can cause a lot of problems in production. I've heard many stories around this. So this problem was solved, again by Google, by a paper they published called asynchronous, like it's for F1 online schema change, asynchronous. So the core idea, which I may not have time to go through, the core idea there is, rather than have a global lock across your entire thing, you want to narrow it down to, let's say, a table level operation. But even that can have substates, which means, let's say state 1, you can only do inserts and deletes, but you can't do reads, for example. And then it moves to state 2. And at any given time, your entire cluster can only work on 2 versions of the schema. And so by managing these states and moving the schema along across these 4 states, you can in parallel do DDL across your cluster with no interruption, no locking. Some of your transactions may fail because they're not allowed to do certain operations on that table during that substate, but that's about it. There is no global lock. And I'll go through that a little bit. And the reason it's required for a distributed database is you cannot lock the entire cluster. It's close to impossible. So you want everything to work, because now you have multiple schema caches across your entire cluster, which you don't have in a single node MySQL. So what MySQL does is it does a single node operation, blocks, it waits for it to finish, and then it externalizes that and puts it on the bin log, and then it goes to the replicas, and then the replicas do have their own problem. And this can cause a lot of replication lag. On a busy system, this is a very big. So people use external tools which read the data and send it across the cluster, and so you have to use all kinds of other, and they have, in the end, none of them can actually overcome the MDL lock. That is required no matter what you do. So yeah, so it's different because you have to make sure that the entire cluster works, because we cannot do a synchronous update of metadata across the cluster. We just can't. Because everyone has cached that information, and so you have to update all those caches and keep them in sync. So you version all the schemas, and so TiDB, as per the original paper, essentially when you connect and you're doing some work, every, I would say, transaction, yeah, it's a transaction, I think, has a lease on the schema. So what that means is that if you can finish your work within this amount of time, the schema is guaranteed to be intact. It could be an old schema, but it is guaranteed to work. The worst case will be that the substate has moved on, and because of the restrictions on that substate, you may have to be forced to roll back or retry. But that's about it. But the rest of your cluster that doesn't touch that table or is not affected by whatever you're doing on that table in that substate, you will proceed perfectly fine. So the granularity is very narrow in this. That is the key point. If you want the full detail, the paper is actually worth reading just on its own. So this is an example. I hope I can explain this in the time. So this is working backwards. So let's say we've finished the schema. It's public now or externalized, and let's say VN. So you can do select, insert, update, and delete. So these are the 4 operations that you may or may not be able to do in the other substates, depending on which substate it is in. That's the key point. And you can a transaction can only work on 2 schemas, versions of the schema at any given time. That's it. And you have a lease, which means if you haven't done your job in the lease on the schema, well then that's it. The schema has expired and the transaction will fail when you try and commit it. So these are the core concepts on which it works. So we are working backwards to this, from where we started, let's say. So let's say you can do everything once it's externalized. In the previous version, you can't do selects, but insert, update, and delete will work. So if your DML is insert, update, delete, it'll work. So now that state is called write only. So what about the state before that? Again, select won't work. There's actually a very interesting reason if you are interested in consistency, so isolation levels. Reads are what cause problems because you've done a read and you've sort of gone and done something with the data. That's why reads are most conservative in this scheme. So you can't read, but you can, I won't go with the details. So one of the things that it's doing in this operation is it can take a snapshot and move it to all the nodes to backfill. That's what backfill is. So when you're writing data, you're writing to a normal LSM, which you can take a snapshot of, it'll take a snapshot of that and move it to the next stage and backfill from there. So insert is always handled. The problematic case is for deletes, and I'll get to it. So when you're in write-only stage, you can do all these things. But delete, update will also work, but the problem in an update is, an update is a delete insert. So the insert will be handled by the backfill, but the delete will not be. So the delete operation has to be done when the DML is being executed. That's the point here. If it's a little confusing at the moment, feel free to ask me afterwards. There's some subtle points here. So now it's changed the value to from R46 to VR. So that's a delete and insert basically, right? So the insert will be fine because that will be moved along in the backfill, but the delete will not be. The delete has to be done. Otherwise, the backfill will not do the delete. It will only do the insert. That's basically what it's saying. So deletes must happen. Updates must happen because they have a delete in them. That's why. They're an insert delete, so that's why the same. But insert at that stage you can't. When the sub-mode or sub-state is delete only, you can't insert. So what does the no in this case mean? So let's assume it worked backwards. It means now the old version is obsolete. Any transaction that had this version when it started, and now the transition has been done to the new schema, they will all start failing. But only once, and then you retry and it should all work. That's the benefit of this scheme. So you have these states, so now you can think and go this way. So you have these sub-states, and each sub-state, you have to decide in this transition which of these operations will work or not. That's the key point here. And deletes have to be handled immediately, whereas inserts will be pushed forward when you move some of the data into the next state. Anyway, you can this is a bit, unless you read the paper, it gets a bit interesting. So you can ask me. I'll be happy to share this. So back to the original thing. So there are other optimizations. We can generate and ingest files. No need to write to the new index in TiDB. It has almost zero impact on. And also with the distributed execution framework, you can easily say, do it on those 3 nodes and all the other traffic can go to the rest of the nodes. And people run like 50, 60, 100 nodes. It's much easier on CPU and I/O. The other thing, the last point there is that it can use the coprocessor inside TiDB to do all this data reading and moving around. It doesn't have to go through the SQL nodes. So it does it at the lower level too. And so this doesn't put any, it reduces the network traffic if it were done through the SQL nodes, because you're operating on large amount of data. You're not really doing much except moving data around from one format to the other, or whatever your DDL is. So all that is pushed down as much as possible into the storage nodes to reduce data movement. So these are some of the timing. So if you have a 10 terabyte index, it can do it in 47 minutes if it's a 1-column key index. If it's a 10-column index, it'll take you 1 hour and 6 minutes. And that's on 10 terabytes. On You can see the config, it's how many PDs, there are 8 PDs and whatever that is. So it scales linearly. So I mean, this is like, these are serious numbers. These are not, toy numbers. So if you want serious scale and you have these problems, you should just go right away and install this and run it. It really is that good. Okay, so now comes to the last slide. So these are all the tools that we have, and they're all open source. And you can easily go and contribute and send us patches for any of these things. It's all open source, no problems. And I'm sure people who work with these sort of things, I haven't. They understand these things more than I do. I work on the database storage side of things. I don't work on the operation side of things. So Sam, my colleague, is here. If you have any questions about any of these, I'm sure he can answer. I don't know much about it. I just know that they exist and that this is how our customers are using it. And you can integrate with, it has great integration through TiCDC, the change data capture. Then there's Lightning that's very useful for importing data from existing systems. So you can import. We have customers who've done, 400 terabytes from Aurora. So, I mean, these tools have all been used to do all those sort of things. So they are battle tested. They're not just toy tools for, 10 megabyte or 100 gigabyte. These are like serious stuff. So you can play with it.
Yeah, a few months ago, we had a 110 terabyte table.
There you go. So, I mean, this is like serious stuff. This is what MySQL people should be working for. And they're just obsessed with HeatWave for some reason, which I don't know what the hell they're on about. But this is how a distributed database should work. And I used to work for MySQL, and I love MySQL, honestly, I do. I still do. Anyway. So yeah, so these are, when we publish the slides, you can hopefully click on these things and the links and get stuff. And that's again in case somebody wants to take a scan of this and win this. And if not, there's also a QR code somewhere there. And so thank you. If you have any questions, please ask me. Yeah, thank you. Anyone? Yeah, sure, please. Sorry, I need, do we have a mic? Oh, I'll just walk up, it's no the paper, the F1 paper, the schema change or the spanner paper? Yeah, so that was the schema online change, F1. I can send it to you now. I mean, I can just give it to you now after this. Sure, that's a Google paper. That's a really good paper. Anybody else? Any question? That's it? Oh, excellent. Thank you. Yeah. Sorry?
Nice presentation.
Oh, thank you very much. Yeah, cheers. Yeah, I'll just, okay. Oh.
Do I now? Oh, I do.
There you go.
See, I'm from Jersey, so when I talk, it's always like I have a microphone on. I was wondering why you came in here. I was like, uh-oh, something's wrong. So anyway, if you don't have a schema, it is sometimes faster for development time, because then you don't have to worry about creating the SQL scripts to add a table or a column, and in some cases, you might need a DBA to verify that the table and column scripts are actually working as they should. It's less verbose than XML, which is saying something, because we all know XML is like this nice, terse language or markup language. Pretty much every programming language can read JSON. And I say pretty much because I haven't used all the programming languages, but every programming language I've used has been able to read it. And I want to make sure I'm covered so somebody can't go, no, well, this language doesn't. And then probably the most important is the fact that some data is unstructured, which is hard for me to wrap my brain around, because I come from a world where data needs to be structured and everything needs to be in a column and there needs to be relations and you need to have data types, and if it's not that way, it's just drives me crazy. But there are some cases where unstructured data exists. You can have configuration data. The example we're going to show, it's configuration data for an application I wrote for a golf league, where yes, the data technically is structured, but I don't need to have it in columns, because I'm never going to query, give me all the golf leagues where the golfers had to pay $10 to join the league. That's never going to happen, so I don't really need to have that in a nice relational table. When I was giving this talk in Montreal last year, somebody said they store exceptions as JSON in the database, and then that allows them to go back and use the JSON functionality to query the exceptions better than they could by looking through the logs. And probably the most important is if your application or what you're doing ingests data from a third-party source, a third-party API, you have no control over the schema that comes back. And if the schema changes, it's going to be a pain in the butt for you to take those changes and throw them into any type of relational structure that you may have set up. So in those cases, I think it makes really good sense to store stuff as JSON. So the way it's done, the way it used to be done years and years and years ago, is developers would store JSON in either a text, char, or varchar data type. It worked. It wasn't great, but it worked. When you search the values, you actually had to use a like search, or you had to use regular expressions to search. And the problem with that is you could get inconsistent results, because if you have nested objects and the parent object and the child object share a key, meaning the key is the same name, doing a like search, it could possibly get results that are different than what you're actually looking for, and the same thing with regex. And then the other problem is, if you updated any value in your JSON document, it updated the entire column. So it was just like doing a regular update. So if you were just throwing text in there, it was the same premise. So in 5.7 of MySQL, the JSON data type was introduced. It's designed to hold valid JSON documents. That's important, because if you try to store something that isn't valid, you'll actually get an error. The data itself is stored in a binary format that has been optimized for replication and quick searches. And also, you can have a defined schema. Now, some people are like, well, if we're using JSON because we don't want a schema, why would we want to make sure that we have a schema? Well, there could be a time where you're logging information from, like the person suggested, you're logging exception information, and you want to make sure that every JSON object you store in this database has a particular key. We can actually set that up when you create the table. You can add a constraint. Another thing is you might want to be, if a particular key exists, I want to make sure it's a number. Or that if it's a date, it's before or after a certain date. Or if it's a number, it's greater than 0. All right, we're going to play a game. And the game we're going to play is called Valid or Not. Here's the rules of the game. I'm going to show you an example of some text. I'm going to point to somebody. That person is going to say valid or not. If you say anything besides those two things, you're wrong. And I'm going to call on somebody else. So it's either valid or not. And if you get it right, you get a lollipop. So you got one already in the back. Valid. Oh, you're going to test me here. Almost. So that is valid, and that is actually just an empty object. So, yay, you got it right. Good job. Next one. You got a lollipop already. Valid. What is that? It's an empty array. Awesome. Heads up. I really got to work on that. You know what it is? You guys are further away than I think. So we got that right. That is valid. What about this? Wrong. It is valid. That is actually valid JSON. Don't ask me why. It just is. What about this? Well, what are you going to say? Not. You're wrong. It's valid. Null is valid JSON. Okay? Well, I'm going to have a lot of lollipops when I'm done. Awesome. What about this? Wrong. Now, what? What'd you say? Single quotes. Texts, dates, and keys need to be in double quotes. So that's why this is invalid. Well, that was fun. I only gave away a couple lollipops. So for the examples we're talking about, so years ago I took over managing a golf league, and I wrote a web application to help me manage the golf league. And one of the concepts in that league is the fact that we have seasons. And each season has a unique set of configuration options. And those configuration options have grown over the years. As I've added more functionality and as we've changed rules in the league, I've had to create new columns in the season table to accommodate them, which became kind of a pain in the ass. Because then I had to update the database, I had to update the getters and setters, and I had to do a whole bunch of stuff just to add one property. And then I realized, you know what, I don't need to do that. I can actually take all the properties that are going to be unique to or that could be unique to a particular season, create them as a JSON object, store that in the database. Then all I got to do is update the getters and setters of what I already have, and if I need to add a new property, I just add getters and setters and be done with it. So this is the scheme I have. You'll see that the one object has a course property, which is an object that has the information about the golf course. Then there is a scoring property that has information about the type of scoring that we use. And we have the subpool property, which is an array of different types of user roles that can actually have, that can play as a substitute in the league. And then we also have use subs, which means whether or not you can use a sub, the league fee, the greens fee, whether or not we use contests, points per hole, golfers per team. There's a lot more. This is just all that could fit on this slide. And I'm not going to go over each one of them. Don't worry about it. So creating a table with a JSON data type is very easy. In your column definitions, you actually specify the data type of JSON. Right there. So we have a column here called season settings, and it's a JSON data type. But what we want to do here is we want to make sure that the league fees property is no less than 0. So what we do is we add a check constraint, and in the check constraint we call the JSON underscore schema underscore valid function, and we pass it this configuration where basically we say the main object the main property, or the main part of the root of the JSON needs to be an object, and that it has to have a property named league fees that is a number, and the lowest value it can be is 0. So if we tried to save a JSON blob where the league fees property was set to -1, it would throw an error. And you see here it says the season settings here is that's where in the JSON schema valid method, the last argument is what column that we're actually going to be using. So inserting JSON, you might think, wow, that's a lot. You know, how do we handle that? Remember, what is JSON? What at its basis, it's a what? String. Who said that? See, you get one now. Yes, we make a good team. It's a string. So that means we can just insert it as if it's a string, just like we would any other string. So whether you're using a JSON object or a JSON string or somebody's first name, we can just do insert surrounded by single ticks. And you'll see here the result of this. If we do select star from season, order by ID, descending limit 1, we'll get the latest item that came in, and you'll see on the end here, it's an empty object like we passed in that insert statement. So before I go any further, I want to talk about some helper functions that we have available to us. These are native MySQL functions. The first one is JSON keys. This function is awesome if you're not familiar with the schema. So you can actually call JSON keys and pass it in the column name that you're looking for, and it will return you an array of all the keys that exist. Now, you'll see up here, by default, you don't have to have a second argument in JSON keys. If you don't pass in an argument, the second argument for JSON keys, it gives you all the keys that are at the root of that JSON object. But in this particular case, we wanted JSON keys for the scoring object. So we do $property name to get the list of keys off of the scoring property, which is off the root of the JSON object. Whenever you're dealing with JSON in MySQL and you see a $, that means you're dealing with the root of the JSON object. There's one exception to that, and we're going to be getting to that shortly. But always remember, $ is the root. So again, here, we're looking for the scoring property off the root. And it's just got the 3 keys, title, description, and handicap type. Now, this is a function that you should only ever use when you're debugging or you're in development. Don't ever use JSON pretty in production because it could really screw up your results. And the reason why is it puts line breaks in the return so that instead of getting one long array, we get them broken down like this so it's a little bit easier to read in the console. So another thing we use, or I use a lot, are path operators. And you'll see why I prefer path operators in a little bit, because I think they're a little bit easier to read and they're a little bit easier to use. And we have 2 path operators, and I honestly don't think they actually have names. So the first one is -. Now the -. is actually a shortcut for calling JSON extract. So if you call JSON extract on a JSON property as we do here, you'd get the same result. And you'll see here again, we do the column name $, course.name. This is actually saying we're going to get the name property off of the course property off the root of the JSON object. But the difference between the -> and the -> is this one will actually return any quotes that may be around the string or around the property value. So if it's a number, it won't have quotes. If it's a string, it will. If we do the -> that's the same thing as calling JSON extract inside of a JSON unquote method or function. And what that'll do is that will actually return whatever's inside the quotes. And I'll show you what that looks like right here. So you'll see here under course name, because we use the -, it returns the quotes as part of the result. Why they did that, I don't know, because I can't imagine anybody would want to use the information in that way, which is why I always use -, which gives me just the text with no quotes. Okay? So, Now we're going to start talking about querying data based on JSON values. So what we're going to be doing is we're going to be returning data from the database based off of the values of certain properties in the JSON object. One method we can use is JSON contains, and you'll see the syntax, whoops, sorry, go back. The syntax is here. JSON contains takes 3 arguments. The first argument is the column that we're talking about. The second argument is the value that we're looking for, and the third argument is the path to that property. So what we're saying here is we want to get the ID, the name, and the league fee, the value of the league fee off the root from season, where the season settings column has a property named league fee that equals 70, okay? And as you already saw, this is going to be the result. Everything comes back where the number is 70. That actually works pretty good, except it works great with numbers and it works great with booleans. It doesn't work great with strings. And the reason why is because in JSON contains, if we want a string, we have to wrap it in quotes. So here, because we're looking for where the core state is equal to WV, we have to say single tick, WV, double tick, single tick for JSON contains when dealing with strings. Yes, I had that same look on my face that you have right now. It's weird, which is exactly why, well, let's show you, this is what the results are. So you see the results are what we would expect. And that's why I prefer to use the path operators to JSON contains or anything like that. And you see here is the same exact query I just showed you, using the path operators rather than using JSON contains in the weird double quoting of stuff. And you know what, let me back up real quick and show you something else here. JSON value is a way that you can actually get the value from a particular property, and you can actually use the returning keyword to say what type of data you want it to return as. So by doing this inside of JSON value, you're basically casting that as a particular value, which I would rather use cast, because that's what we're doing, and it's less confusing. So you see here, we're casting the value of greens fees as decimal with 4 spaces and 2 after the decimal, and then we have where the core state property of season settings equals WV. To me, that's a lot easier to read and a lot easier to parse quickly than what we saw with JSON contains in the double quotes. Because I don't know about you, but when I see double quotes like that, I start to go, whoa, something's wrong. And that's exactly when the first example I saw JSON contains, I'm like, this has got to be a typo, but it's not. So my suggestion is going to be, if you ever want to get to a value of a particular property in your JSON object, use the path operators. And use hyphen greater than. Don't use the other one, because the other one leaves stupid stuff in there when you have strings. And then here's what the values look like. You can see that it's actually cast as 2 decimal spaces. So, as I said before, when you have a JSON object, one of the properties or the actual JSON object itself could be an array. And there is a function we have available to us that will allow us to query that array as if it is a table. And that is called JSON table. So what we're doing here, and this gets a little complex. So you see at the top we're doing select ID and name from season, but we're also calling group concat on a property called sp.roles. You'll see SP doesn't exist in the from statement initially. But then we go down here to JSON table. So as I said, what JSON table does is it will actually allow us to create a join between our table that we're dealing with and the values of an array inside of each JSON object in every row in the database. And this takes a couple of arguments. The first one, is the column that we're using. So here you'll see we're doing s.season settings because I aliased that with s because it was a lot of typing and stuff went off the side. The second argument is the path to the array that we want to use. And in this particular case, we want to use every element, that's what the star inside the brackets is, for the property named subpool that is off the root of the object. And then the second part of this, or the last part of this, is we have a columns definition. So we use the keyword columns, and then we pass in the name that we want to use. So the first part is the name. The second part is what data type we're going to use. And then the path. And you'll see here, the path is $.type. Remember I talked about earlier that $sign always represents the root of a document except for one case? This is that case. When you're using JSON table and you're specifying your columns, the $sign is the root of the particular item you're looking at in the array, not the JSON document itself. So we have a property called type that is inside of every object in our subpool array, and that's what this means. And then we have role, again we set it as varchar 20, we set the path to .name. And then here, we have to alias it. Whenever you use JSON table, you have to use an alias. If you don't, it'll throw an error. Okay? So that's where the SP comes from. That's where this group concat sp.role comes from. And then we go, in the where clause, we say where the subtype, so this column, equals role, and then the core city, which is part of the season settings, is equal to Charlestown. And then we group all those together so that we get the group concat will work. So we say we want to group it by the ID of the course. And then when we run this, you'll see that for the first group, there's just one role. But for these last two, there's multiple roles. And each one of those came from a particular element inside of the array of the property named subpool. JSON table is very, very, very helpful if you need to search through data that's in a JSON array, because you can do like what I just did and say where a value in the array equals this. So updating JSON values. There's 3 ways that we can update the values of JSON properties in a JSON document. The first is JSON insert. JSON insert will insert a new key into a JSON document. It will not update the value if the key already exists. And you can actually add multiple keys in a single method call. So if you have, or a single statement, so if you have a bunch of different values that you need to update, you can just call JSON insert once and it'll handle multiple instances of that. So then we have JSON replace. JSON replace will update a value of existing keys in a JSON document, but it will not add them. So if you call JSON replace and you specify a property that doesn't exist in a particular JSON document, it won't add it. And again, you can add multiple keys in a single statement. And then lastly, and this is the one I tend to use most, JSON set. It inserts and updates. So if the key already exists, it adds the new value you pass in. If it doesn't exist, it creates it and sets the value. And it's not on here, but you can probably imagine, yes, you can do multiple at one time in one call. So let's show some examples. So here's JSON insert. And you'll see what we do here is we do update season, set season settings equals JSON insert, season set JSON insert. The first argument is the column we're using, so we do season settings. And then we're going to insert the, whoops, I did it again. We're going to insert a league fee property, and we're going to set it to $25.5. So in this middle example, this is the season that we just created in the beginning where we put in an empty JSON object. So now we have a league fee of 25.5, but you'll see over here in an existing one, the league fee stayed the same. It didn't get updated. JSON replace. JSON replace pretty much takes the same arguments where the first argument is the column we're going to use, the second argument is the property that we want to replace, and then the last argument is the value. Again, in our new property you'll see, or our new league season rather, you'll see that the golfers per team value doesn't exist, but the golfers per team value over here was set to 4. And then on JSON set, again, we pass in the column name, the property we want, which again, we're going to do golfers per team, and we're going to set it to 2. And you'll see here in the new one that we created, the golfers per team now exists. And over here, it set it back to 2. JSON set to me is it's a little bit better because you don't have to worry about, you know, does it exist, does it not exist? You can just set it and take care of it. And then we can remove properties from a JSON object using JSON remove, where the first argument is the column name, and then the second argument would be the property or the path to the property we want to remove. You'll see here now that the golfers per team is removed from there, and it's removed from there as well. When you actually do update statements like this, you don't have to do global stuff like I did here. You can actually add a where clause. I just didn't for the sake of this demonstration, or these demonstrations. So this, I think, is actually really cool in the fact that if you have relational data inside of a table that also has JSON data, you can return all the stuff as JSON. And the first way we can do that is with a method called JSON object. JSON object takes pairs of arguments. So if you're using JSON object, you have to have a number of arguments that is evenly divisible by 2. If you don't, you'll get an error. In each pair, the first argument is the name of the key you want returned. The second argument is the value. So if you see here, we call JSON object, we're going to have a parameter called ID that is equal to the value of the ID column, a parameter called name, or a key called name, which is the name column, then we have the start date, and then here we have a property called settings, but we're returning the season settings, which if you remember, is a JSON object to begin with. And this is what that would look like for the league that we just created, where we only have that one setting in there. So it's smart enough to realize that when we're returning JSON, to return it as JSON when you're using JSON object. JSON array ag. I tried coming up with good examples for JSON array, and I really couldn't, because everything I wanted to do was usually the result of trying to aggregate values from other stuff. So what JSON array ag does is it will actually create an array of values based off of results, and it groups them. And you don't actually have to use a group by for this in this case. So here we say JSON array ag, and then inside that we have a JSON object. So this tells me right away that we're going to be returning an array of JSON objects. Okay? And inside that object we have the ID, the name, and the start date. And then we have from season, where ID is greater than 22, and we order it by the start date, descending. And this is what our result will be. It's actually just an array, you can see from the top and bottom, of the objects that we specified. Array ag also comes in handy if you have a table that you have a parent-child relationship with, and you want to return multiple child data inside of one row, or inside of one JSON object from the parent. So you can actually use array ag on the child data inside of a join, or with a join, I should say. So this is all good. Being able to search properties on JSON like this, I think is awesome. But it's expensive. Even though it's been optimized for searching, it's expensive to go through each of the objects in a row, especially when you consider the fact that each document can be up to 1 gigabyte in size. So each JSON object column that you have can support, each row can support up to 1 gigabyte of data. Now think about how big or how much data 1 gigabyte of JSON data is. That's pretty insane. Now imagine you have a system that has even half that size, but there's tens of thousands of rows, and you need to search by a particular property. There's going to be a performance hit there. Fortunately, we can index JSON data. So we can actually create an index on a JSON column that is for a particular property. Now, has anybody here played with MySQL document store? Woo, awesome. So inside of the document store API, there's actually there's a method called create index. That actually follows a different path that I'm showing you here because it has to be backwards compatible with earlier versions. This example that I'm going to show you uses a functional index, which if I remember correctly was first introduced in, I want to say, 8.0.13. So the first thing we're going to do is we're going to run a very simple query. We're going to run an explain plan on a very simple query. We're going to select everything from season where the course, or the city name of the course in the season settings property is equal to Charlestown. And this is what we get. And the important thing we want to look for here is the possible keys and the key values. If we had proper indexes on this particular table, then those would actually be populated with the indexes that it would use. So the way we create an index, and this is when we're doing a functional index. If you do create index using the API for MySQL document store, it actually creates a generated column and then creates an index off of that. This, we're doing it differently. We're actually creating a functional index of the data. So the first thing we need to do is we need to call cast. And the reason why is, remember I told you the path operator is just a shortcut for JSON extract inside of JSON unquote. JSON extract returns a data type of text. What can't you do with data type of text? You can't index it. So our functional index, we actually have to cast whatever is returned from the course settings where we're getting the course.city as char. In this particular case, I picked char 100. Was it overkill? Yeah, probably. I don't know too many city names outside of any place in Wales that would have 100 characters, but that's the way I did it. And then you see the last thing we need to do here is we need to set the collation to UTF-8 MB4_bin. And the reason why that is because the values returned from JSON unquote are collated as UTF-8 MB4_bin. If you don't do this, the index will be created. It just won't be used because the collations don't match. So after we create the index, we do show indexes from season, and you'll see now we have it's the second row because the first one is the ID. I didn't want to put that up there. And you'll see down here, you can actually see what the expression is, and you can see here where it actually changed that path operator to JSON unquote JSON extract. And then if we go back and we recheck the explain plan, you'll see now it's actually showing it's using the index that we created. That's actually pretty cool. I actually like that a lot. And could I have created that index using the way it does in the document store API by first creating a generated column and then creating the index? Yeah, but I couldn't do it in one statement. I wanted to show you how you could do it in one statement. So for anybody who's interested, this URL here will take you to the documentation for the, it'll take you to the JSON function reference for MySQL. Everybody good there? I still see a couple phones up. You want me to keep them out? There's another one coming next. Good? Okay. So one of the things that we as the community team have been able to do is we work with Oracle University. If you've never heard of Oracle University, that's the group that manages the Oracle certifications as well as any training responsible for those certifications. We actually have an agreement with Oracle University that whenever we speak, we can actually offer free training or free certifications to the people who attend our sessions. This fits right into my giving away free stuff because I don't have to pay anything for it. But if you scan this QR code, you'll be brought to a page where if you already have an Oracle account, you can use that to sign in. If not, you can create one. And then this is actually a relatively new process. So please bear with the people who get this information because I don't get it because once you take the screenshot and go to the URL, I'm done. I've done my job. And it will actually, I forget how much it is. I want to say it's $200. It could be less than that. But basically, you have 2 months to take any type of training that you can that would match that or register for a certification exam. And it's free. It won't cost you anything. Except for the fact that Oracle has your information. Sorry, can't help you there. So, wow, I did pretty good considering we stopped pretty late, or started pretty late. Does anybody have any questions? That means either I did a really good job or I did a really bad job. I'm going to go with the former because I have a very fragile ego. So, now it's time to give away the free stuff. And again, I didn't pay for this, so I don't really care. I told you guys you need to pay attention to everything I say, everything you see. How much does my dog weigh? What was that? 106 pounds. You want the hat or you want the dolphin? This is not going to go very far. See? Wow, that was like Donovan McNabb. All right, so the next question is, how many babies have I delivered? You had your hand up. 3. And that is why I don't play baseball. If nobody has anything else, our time here is done. Thank you for spending the last part of the day with us, or with me. I appreciate it. And you guys have a great rest of the conference.